I was looking up. The Milky Way stretched across the sky like someone had spilled milk across black velvet, and I remember this thought hitting me, just hitting me like a physical thing, that every single one of those dots was a sun with planets around it, planets that could have people on them, people looking back at me through their own night sky. I asked my dad that night, if there's so many stars, why haven't we seen anyone yet? He didn't have an answer. But that question, it never left me. For years, I thought it was a simple problem, a math problem. There are billions of galaxies. Each galaxy has billions of stars. Some of those stars must have planets. Some of those planets must have life. It's not even close to reasonable to think we're alone. The numbers don't work. Except we've been listening. Really listening. For decades, with the most sensitive equipment humanity has ever built. Pointed at the cosmos, waiting for a signal. A whisper. A hello. And we've heard nothing. That silence is the loudest sound in astronomy. And what it really means, is something that keeps scientists awake at night, even if they won't admit it publicly. This is the story of why we haven't found aliens yet. But more importantly, it's the story of what that silence tells us about ourselves, about life, and about our place in a universe that might be far stranger and lonelier than we ever imagined, or maybe more crowded than we'd like to believe. The answer isn't what you think it is. And by the end of this, you won't be able to stop wondering about it. Let's start with the math. Because the math is the thing that made everyone so sure we'd have found something by now. In 1961, an astronomer named Frank Drake wrote down an equation. Seems simple, right? Just multiply some numbers together. But this equation, the Drake equation, it's haunted science for 60 plus years. It's like the equation that proved we should have found aliens already. It's the equation that made us confident enough to build massive telescopes and point them at the sky and say, "Come in, neighbors, we're listening." Here's how it works. The equation estimates the number of communicative civilizations in our galaxy, and it does it by breaking down the problem into smaller pieces, manageable pieces. First, how many stars are in our galaxy? Well, we know that one, roughly 100 to 400 billion. Let's say 200 billion to be conservative. Next, how many of those stars have planets around them? For a long time, we had no idea. This was the missing piece. But then, starting in the 1990s, we started finding exoplanets, thousands of them, and the data became clear. Most stars have planets, like most of them. We're talking 70, 80, 90%. Some stars have whole systems, multiple planets orbiting them like our solar system. So now we're not talking about a handful of planets in the galaxy. We're talking about tens of billions, maybe hundreds of billions. Next question. Of those planets, how many are in the habitable zone? This is the Goldilocks zone. Not too close to the star. Too hot. Water evaporates. Life fries. Not too far away. Too cold. Water freezes. Life hibernates permanently. Just right. Close enough to get warmth and energy. Far enough to keep liquid water stable on the surface. And here's where it gets interesting. Because the habitable zone isn't tiny. It's not some razor-thin band of distance. It's actually pretty wide. And when we look at our galaxy, when we run the numbers, we find that billions of planets probably sit in that zone. Then the equation asks, of those habitable planets, how many actually developed life? This is where it gets philosophical, because we only have one data point, Earth. Life emerged here. We don't know if that was a miracle or inevitable. But let's be generous. Let's say life emerges on even a small fraction of habitable planets. Let's say 1 in 100 or 1 in 1,000. You're still talking about millions of planets with life on them. Then the next step, of those planets with life, how many developed intelligent life? Language, tool use, civilization. Again, we only have one data point, but some scientists argue that intelligence is an adaptive strategy, a really good one. So maybe it emerges more often than you'd expect. And finally, of those intelligent civilizations, how many developed communicative technology, radio broadcasts, laser signals, something we could detect? And how long do those civilizations last before they destroy themselves or move on to something else? Frank Drake himself, when he ran the numbers with reasonable assumptions, came up with something like 10,000 communicative civilizations in our galaxy right now. 10,000. Think about that for a second. 10,000 alien civilizations. Some older than us, some younger, some so advanced that their technology would look like magic to us, all sharing the same galaxy, all aware that they're not alone. If that number was right, we shouldn't be here talking about silence. We should be drowning in signals. We should have picked up a stray transmission decades ago. A radio broadcast, a television signal leaking into space. Something. But we haven't. And that's the paradox that eats at everyone in this field. Enrico Fermi, another physicist, walked into a room in the 1950s and asked the question that would define the next 70 years of thinking. Where is everybody? It's a simple question, almost childishly simple, but it's the most profound question in science, and nobody has a good answer. This is the Fermi Paradox. And to understand it, you need to understand what makes it so unsettling. Let me take you back to that field where I was 12, lying on my back, staring up. I didn't know the Drake equation yet. I didn't know the Fermi Paradox, but I understood the basic logic. There are a lot of stars. Life happened here, so life should happen out there too. Probably a lot of life. As I got older, I learned the numbers. I learned the equations, and they all pointed the same direction. We should have found something, but here's what nobody tells you when you're a kid looking up at the stars. They don't tell you that the silence is louder than any signal could be, because silence means something. In 1974, we sent the first intentional message to aliens. It was called the Arecibo message, sent from Puerto Rico, from this massive radio telescope built into a sinkhole. The message was encoded, a picture of a human figure, our solar system, the structure of DNA, the numbers 1 through 10, a greeting, we're here, we exist, we're intelligent. We sent it toward the star cluster M13, which is 25,000 light years away. It won't arrive for 25,000 years. And even if there's someone there, even if they receive it and immediately send back a response, we won't hear it until 50,000 years from now. That's longer than modern humans have existed. So in a real sense, we sent that message into the void with no expectation of hearing back. It was a symbolic gesture, a bottle thrown into the cosmic ocean. But here's the thing. We've been listening to the cosmic ocean for decades, and the bottle hasn't come back. Nothing has. In the 1990s, a project called the Search for Extraterrestrial Intelligence, SETI, started using radio telescopes to systematically listen to signals from space. They developed a protocol, ways to recognize a signal that couldn't possibly be natural. They listened for patterns, for structure, for the unmistakable fingerprint of intelligence. And they've been listening for 30 years now, continuously, with increasingly sensitive equipment, more powerful computers, better algorithms. The signal to noise ratio has gotten better. Our ability to detect faint signals has gotten better. The equipment has gotten more sophisticated. We should be finding things, but we keep finding nothing. That's not quite true. In 1977, there was something called the wow signal, a strong narrowband radio signal detected by a radio telescope in Ohio. It lasted 72 seconds. The astronomer who found it circled it on the printout and wrote "wow" in the margin. People got excited. This could be it. This could be the signal we've been waiting for. But when they tried to find it again, it was gone. They never detected it a second time. It's still unexplained. Some people think it was an alien signal. Others think it was a satellite or a pulsar or just interference. We still don't know. And that's kind of the perfect metaphor for this whole thing. One tantalizing hint. One moment where we thought maybe, just maybe. And then nothing. The silence returned. I remember the day I really understood that silence. I was in college. I'd chosen to study physics partly because of that field, that night sky, that question my dad couldn't answer. And I was sitting in a cosmology class, and my professor, this brilliant guy who'd spent his whole career looking for signals, he said something that stuck with me. He said, the universe should be noisy. It should be loud with civilizations. And instead, it's quiet, completely quiet. And we don't know why. And then he paused. And he looked at the class. And that should terrify you. I didn't understand why he said that then. But I do now. Let's talk about what we know. What we've actually found. Because the story of why we haven't found aliens yet isn't just a story about silence. It's a story about everything we have learned about planets, life, and the universe. In 1995, something changed. A Swiss astronomer named Michel Mayor and his graduate student Didier Queloz were using a telescope to observe a star called 51 Pegasi. And they detected something. A wobble, a tiny regular wobble in the star's motion. A planet was orbiting it. This was huge. We theorized about exoplanets, planets around other stars, forever, but we'd never actually confirmed one. And now we had 51 Pegasi b. That's what they called it. A hot Jupiter, a massive gas giant orbiting incredibly close to its star. So close that its year lasted only 4 days. The surface temperature would be in the thousands of degrees. But it existed. It was real. Confirmation that our solar system wasn't special, that planets were common. Since then, we found over 5,000 exoplanets, and the number is growing fast. Each year, we find more. The James Webb Space Telescope, launched in 2021, has been finding them at an accelerating rate. And here's what we've learned. Planets are everywhere. They're not rare. They're not exceptional. They're the normal state of affairs. Most stars have planets. Most stars have multiple planets. Our galaxy probably has more planets than stars. That's how common they are. And the habitable zone ones, the ones where liquid water could exist, scientists estimate there could be 40 billion Earth-sized planets in habitable zones just in our galaxy. 40 billion. That's not a metaphorical number. That's not a guess. That's based on actual observational data from thousands of exoplanet discoveries. So the first filter in the Drake equation, the one about how many planets exist in habitable zones, that's solved. There are tons of them. But here's where it gets weird, because we've also learned something else. We've learned that just because a planet is in the habitable zone doesn't mean life will emerge there. In fact, what we've discovered is that the conditions required for life to emerge, and then for that life to survive, are incredibly specific. Let me give you some examples. First, a magnetic field. Earth has one. It's generated by the churning liquid iron in our outer core, and it does something crucial. It deflects the solar wind, that constant stream of charged particles coming from the sun. A planet without a magnetic field gets bombarded by that solar wind. Over time, it strips away the atmosphere. Look at Mars. Mars is half the size of Earth. It used to have a thicker atmosphere, thicker water cycle, maybe even surface water, but Mars cooled down faster than Earth did. Its core solidified, the magnetic field shut off, and then the solar wind ate away its atmosphere. Over billions of years, Mars went from being potentially habitable to being a frozen desert. Now, generating a magnetic field requires a specific size, specific internal structure, specific rotation rate. Not every planet will have these. Second, plate tectonics. Earth has them. Our crust is divided into plates that slowly move around. They collide, they separate, they slide past each other. And this process, this geological dance, it's actually crucial for life. Here's why. When plates collide, they create mountains. Mountains trap moisture, create weather patterns, regulate climate. When plates separate, they create rift valleys where new crust forms. This volcanic activity brings nutrients up from the interior, nutrients that end up in the soil, that plants need, that become the foundation of the food chain. Plate tectonics also recycles carbon. Through a process called the carbonate-silicate cycle, carbon dioxide gets locked into rocks, gets buried, comes back out through volcanic activity. This regulates atmospheric CO2, which regulates temperature, which keeps the planet in a habitable range. Sounds simple, right? But plate tectonics is weird. Most planets probably don't have it. You need a planet that's large enough to have a molten interior, but not so large that it becomes a gas giant. You need it to be cooling down, but not too fast. You need the right composition, the right density, the right water content. Earth basically won the lottery on this one. Third, a large moon. We have one, the moon, and it does something crucial. It stabilizes Earth's axial tilt. Earth's axis is tilted about 23.5 degrees relative to the plane of its orbit. This tilt is what causes seasons. And it's stable because the moon is there, exerting a gravitational influence that keeps the tilt relatively constant. Without the moon, Earth's axial tilt would wobble. A lot. It could swing from almost no tilt to extreme tilts. 50 degrees, 60 degrees. And that would cause wild climate swings, extreme seasons, ice ages that come and go rapidly. The climate would be chaotic. Life needs stability. It needs to be able to predict seasons, adapt to them, plan around them. Chaotic climate would make that harder. And here's the thing about the moon. It didn't just appear. It formed from a collision. About 4.5 billion years ago, a Mars-sized object smashed into Earth. The impact was catastrophic, but it ejected material into orbit, and that material coalesced into the moon. It was a cosmic accident, a 1 in a billion chance event that created the conditions for complex life. Fourth, Jupiter, our solar system's gas giant. It orbits in the outer solar system, and it does something crucial. It shields us. Its massive gravity well attracts comets and asteroids that would otherwise rain down on the inner planets. Without Jupiter, Earth would be constantly battered by impacts. Large impacts. The kind that would keep sterilizing the planet, killing life, forcing it to start over. With Jupiter acting as a shield, we get fewer impacts, fewer extinction events, more time for life to evolve. Again, not every planetary system has a Jupiter. And even if it does, the Jupiter might be in the wrong place. It might have migrated inward, destabilizing the inner planets. It might be in such a wide orbit that it doesn't shield anything. So when you add all of this up, the magnetic field, the plate tectonics, the large moon, the protective gas giant, you realize that Earth isn't just special because it has life. Earth is special because it has the right combination of planetary characteristics to allow life. And each of these characteristics is relatively rare. This is what scientists call the rare Earth hypothesis. Proposed by Peter Ward and Donald Brownlee in 2000, it argues that complex life, the kind of life that could develop civilization, technology, radio signals, might be far, far rarer than the Drake equation suggests. Not because life itself is rare. Life might actually be pretty common. But complex life, intelligent life, that might be incredibly rare. Because even after a planet gets all the right conditions to allow life to emerge, life then has to actually emerge. And then it has to survive. And then it has to evolve into something intelligent. Each of those steps has its own probability. And probabilities multiply. So if each step has, say, a 10% chance of happening, then 10% times 10% times 10% equals 0.1%. And if there are more steps than that, which there are, the probability drops exponentially. So maybe intelligent life isn't common. Maybe Earth is the statistical anomaly. Maybe we're one of the only intelligent civilizations in the galaxy. Or maybe we're the only one. That's a wild thought. The only thinking beings in 100 billion stars. The only voices in the cosmic silence. But it's not as wild as it sounds when you start looking at the data. Let me tell you about something called the Great Filter. The Great Filter is a concept that comes from thinking about the Fermi Paradox. If the universe should be full of intelligent life, but we see no signs of it, then there must be some barrier, something that prevents life from achieving intelligence and spreading out into space, something that's hard, really hard. That's the Great Filter. And the terrifying part is that we don't know where it is. It could be behind us. Maybe the emergence of life itself is incredibly difficult. Maybe the conditions required are so specific that it only happens in a tiny fraction of planets. That would mean we're incredibly lucky to be here. It would mean intelligent life is rare, but not impossible. But it could also be ahead of us. Maybe life emerges pretty easily. Maybe intelligence evolves regularly. But maybe there's a step that kills civilizations. Maybe every civilization reaches a certain level of technology and then destroys itself. Nuclear war, biological warfare, artificial intelligence that turns against its creators, climate collapse, some filter that wipes out civilizations right before they could spread out into space. If that's the case, then Earth is on a trajectory toward that filter, and we're going to hit it. Unless we figure out how to get past it. And if that's true, then the silence makes sense. We see no aliens because no civilization makes it past the filter. This is why my professor said the silence should terrify us. I spent a lot of time thinking about this in college. Too much time, probably. I'd lie awake at night thinking about filters, about what could be the barrier between life and cosmic civilization. And I realized something. I realized that trying to figure out what the Great Filter is was probably the most important question a human could ask. Because the answer would tell us everything about our future. Let me back up for a second. I want to talk about what we know about how life actually emerges. For a long time, we had no idea. Life just seemed to happen. God made it, or it appeared spontaneously. No one really knew. But in the 1950s, two chemists named Stanley Miller and Harold Urey did an experiment. They recreated what scientists thought Earth's early atmosphere was like: methane, ammonia, hydrogen, water vapor. They added some energy, electrical sparks, to simulate lightning, and they let it run for a week. When they analyzed the results, they found amino acids, the building blocks of proteins, building blocks of life. The experiment suggested that under the right conditions, the organic molecules of life could form spontaneously from non-living chemistry. This was huge because it meant that the emergence of life wasn't miraculous. It was just chemistry. Given the right conditions, it would happen. But here's what happened over the next few decades. As we studied the early Earth more carefully, we realized the atmosphere probably wasn't what Miller and Urey thought. The conditions were different, and when you run the experiment with more realistic early Earth conditions, you get fewer organic molecules. The process is slower, less efficient, which brings us back to the question, how likely is it that life emerges? We have one data point, Earth, and life emerged here about 3.5 to 4 billion years ago, pretty quickly after the planet formed. Does that mean life emerges quickly everywhere? Or does it mean we got lucky? The truth is, we don't know. We only have one example, but here's what we do know. We know that Earth has been through some rough patches, and life survived them. About 2.4 billion years ago, something happened called the Great Oxidation Event. Photosynthetic bacteria started producing oxygen as a waste product, and oxygen accumulated in the atmosphere. This was catastrophic for most life at the time because oxygen was toxic to anaerobic organisms. It's called the oxygen catastrophe. It nearly wiped out life on Earth. But life didn't go extinct. Life adapted. New organisms evolved that could use oxygen, and oxygen became the foundation for more complex life. Then, about 600 million years ago, there was the snowball Earth event. Evidence suggests that the entire planet froze over. Ice covered the equator. Glaciers extended into the tropics. The planet looked like a giant snowball. How long did this last? Millions of years, probably. And life survived it. Probably in small refugia, tiny areas of liquid water, maybe near hydrothermal vents, where life held on. Then about 66 million years ago, the asteroid that killed the dinosaurs hit. A 10-kilometer rock slamming into the planet. The impact created a fireball. Dust blocked out the sun. Temperatures dropped. Ecosystems collapsed. But life survived. Mammals survived. Birds survived. Life recovered. The point is, life on Earth is resilient. It's been through catastrophes that should have ended it. But it didn't. It kept going. What that tells us is that once life emerges and gets established, it's hard to kill. Life is stubborn. Life is opportunistic. Life finds a way. So maybe life emerges fairly easily. Maybe it's not the great filter, but then we have to ask, what about intelligence? I want to take you on a little detour here, because understanding intelligence on Earth is key to understanding what we might expect to find out there. Intelligence is weird. It's not like eyes or wings or teeth. Those are straightforward adaptations. You develop better eyesight, you can see better, you survive better, you reproduce more, genes for better eyesight spread. But intelligence is strange. It's metabolically expensive. A big brain uses a lot of energy. It's slow to develop. Humans take 18 to 20 years to reach adulthood. And for a long time, it's not clear that it provides a survival advantage. A gazelle doesn't need to be intelligent. It needs to be fast. A lion doesn't need to be intelligent. It needs to be strong. A cockroach doesn't need to be intelligent. And yet, cockroaches have been around for 300 million years. So why did intelligence evolve at all? The answer is complicated, but a big part of it comes down to social living. Many animals live in groups, and in a group, it's advantageous to be able to understand other minds, to predict what others will do, to cooperate, but also to compete for status. Intelligence gives you an edge in that competition. You can form alliances. You can manipulate others. You can plan ahead. Great apes are intelligent. Dolphins are intelligent. Elephants are intelligent. Corvids, crows, and ravens are intelligent. And what do they all have in common? They're social animals. They live in groups with complex hierarchies and relationships. But intelligence in humans is different. It's so extreme that it seems almost like overkill for the normal challenges of survival. Humans can do mathematics. We can contemplate the nature of consciousness. We can create art for no survival benefit. We can wonder about things that have nothing to do with reproduction or survival. This extreme intelligence might be a byproduct, a side effect of having brains that evolved for social competition but ended up with way more capacity than necessary. Or it might be something else, something specific about our environment, our evolutionary history that pushed our ancestors toward more and more intelligence. There's a hypothesis called the aquatic ape hypothesis that suggests our ancestors spent time in water and that aquatic environments favor intelligence. Water is three-dimensional. You have to navigate three-dimensionally. You have to hunt in three-dimensional space. That requires more sophisticated cognition, or maybe it was tool use. Our ancestors started using tools, and using tools requires understanding cause and effect. You need to visualize a tool before you make it. You need to understand how it will work. Tools and intelligence co-evolved. Or maybe it was language. Language is uniquely human. Most animals have communication, but not language. Language requires a specific neural architecture, and once you have language, everything changes. You can transmit knowledge across generations. You can plan for the future. You can build on previous discoveries. Language might be the key to intelligence. And language might be incredibly rare. Here's what we know. Modern humans have had language for maybe 100,000 years. Before that, our ancestors had much simpler communication. And before that, there was no language at all. We don't know exactly when language emerged, but we know it's relatively recent in our evolutionary history. And we know it's unique to humans. No other animal has anything close to true language, which suggests that language, real, complex, grammatical language, is hard to evolve. It requires specific neural structures. It requires a specific kind of vocal apparatus. It requires a lot of things to come together just right. And once you have language, intelligence explodes. Because now knowledge can accumulate. Now ideas can build on previous ideas. Now a single generation can make discoveries that would take countless generations without language. So maybe the filter is language. Maybe intelligence evolves sometimes, but true language, the kind that allows for civilization, is incredibly rare. I spent a whole semester in college studying animal cognition. I read every paper I could find about corvid intelligence, elephant self-awareness, dolphin communication. And the more I read, the more convinced I became that something about human language was fundamentally different. Crows can solve complex problems, but they can't tell another crow about their solution in a way that the other crow understands and can apply to a new situation. They can't build a tradition of knowledge. Dolphins have sophisticated communication, but they can't use their clicks and whistles to describe abstract concepts. They can't create art for its own sake. Humans can do all of this. And it all traces back to language. So maybe that's the great filter. Maybe life is common, intelligence is common, but language, real, symbolic, grammatical language, is rare. And civilizations can only emerge once you have that level of language. If that's true, then intelligence alone isn't enough. You could have thousands of intelligent species in the galaxy, but very few of them would have language, and even fewer would develop civilization. That would explain the silence. But let's assume we get past that filter. Let's assume language emerges. Let's assume civilization develops. Now what? Now you have technology. Now you have the ability to manipulate your environment, to harness energy, to build things. And this is where things get really interesting, because technology brings new problems. A civilization that develops to the point where they can make radio broadcasts, that's a civilization that's achieved industrialization. They're burning fossil fuels. They're creating pollution. They're changing their atmosphere. In other words, they're probably dealing with climate change. Every civilization that reaches the industrial level probably faces an existential crisis. Because industrialization requires burning ancient carbon, fossil fuels, which releases carbon dioxide into the atmosphere, which traps heat, which changes the climate. If a civilization doesn't figure out how to manage that, it collapses. If it does figure it out, it has to transition to renewable energy. It has to remake its entire energy infrastructure. That's not easy. That takes political will, international cooperation, a willingness to sacrifice short-term profit for long-term survival. Some civilizations might not make that transition. Some might destroy themselves through climate change. Then there's nuclear weapons. Once a civilization develops nuclear fission, they can create weapons that can destroy entire cities. And the logic of nuclear weapons is terrible. It's based on mutually assured destruction. You build more weapons to deter others from attacking you, but this creates an arms race. And in an arms race, there's always the possibility of miscalculation, of an accident, of a war that destroys civilization. We've come close. In 1983, during the Cold War, a Soviet early warning system falsely reported that American missiles were incoming. A Soviet officer named Stanislav Petrov was supposed to report this of the chain of command, which would have triggered a nuclear response. He didn't. He reported that it was probably a false alarm. And he was right. If he'd reported it as a real attack, we'd probably be living in a nuclear winter right now. Humanity would be in serious trouble. We only survived because one person made the right call. Because of luck, and that's not the only time we've come close. There have been multiple incidents where nuclear war almost happened by accident. So maybe that's a filter too. Maybe every civilization that develops nuclear weapons has a certain probability of destroying itself through nuclear war. And maybe that probability is high enough that it filters out most civilizations. Then there's biological warfare, and artificial intelligence, and nanotechnology, and whatever comes next. Each new technology brings new risks, new ways for a civilization to destroy itself. And as technology advances, those risks get more severe. A civilization with advanced biotechnology could create an engineered pathogen that kills billions. A civilization with advanced AI could lose control of their artificial intelligences, which could decide that humans are obstacles to their goals. So maybe the great filter is something we haven't encountered yet. Maybe it's a technology that's so dangerous that most civilizations that develop it end up destroying themselves. This is bleak thinking. I know, but it's the kind of thinking that keeps astrobiologists up at night. Because if this is true, if civilizations regularly destroy themselves through the technologies they create, then the silence makes perfect sense. The universe isn't full of aliens. It's full of ruins, dead civilizations, species that made it to the industrial level and then destroyed themselves. And we're probably on the same trajectory. I want to tell you about a moment in my life that changed how I thought about this. I was 23, finishing my undergrad degree in physics, and I was depressed, really depressed. Not in the clinical sense, though maybe that too, but philosophically depressed. Because I'd spent 4 years studying the cosmos, learning about the vast scales, the incomprehensible distances, the billions of galaxies. And I'd spent that same time studying the Fermi Paradox, the great filter, the possibility that we might be alone. And I couldn't shake the feeling that it was all pointless. That intelligence was a cosmic accident. That civilization was a brief candle that burned bright and then went out. I remember sitting in my apartment looking out at the city lights and thinking, what's the point? What's the point of doing anything if it's all going to end anyway? And then my mom called. She was worried about me. She'd noticed I wasn't myself. I tried to explain it to her. This existential dread I was feeling. This sense that we might be alone in the universe, that our existence might not matter in the grand scheme of things. And you know what she said? She said, so what? Just like that. So what? And at first I was annoyed. I thought she wasn't taking it seriously. But then I thought about it more. And I realized she was right. So what if we're alone? So what if intelligence is rare? So what if our civilization might eventually destroy itself? None of that changes what's true right now. Right now we exist. Right now we think. Right now we can understand things. We can create things. We can love each other. The fact that it might not last forever doesn't make it meaningless. In fact, maybe it makes it more meaningful. Because meaning isn't something that's supposed to be eternal. Meaning is something you create in the finite time you have, with finite resources available to you. That conversation with my mom pulled me out of a dark place, and it changed how I thought about the silence. The silence isn't a verdict on our worth. The silence is just silence. It's an absence of signal. And the absence of signal doesn't tell us whether we're special or worthless. It just tells us that we need to keep looking. So let's talk about what we're actually looking for. What does a signal from an alien civilization would look like? For a long time, people assumed it would be radio waves, intentional broadcasts, maybe in the microwave range because that's a frequency that travels well through space and isn't absorbed by interstellar dust. SETI scientists developed a protocol for what to look for. They'd be looking for patterns, narrow band signals, signals that contain very little power, concentrated in a thin slice of the spectrum. That's a clear sign of intelligence because natural sources, pulsars, cosmic radiation, whatever, they produce broad spectrum signals. Intelligent beings would concentrate their power in a narrow band to make it easier to detect. They'd also be looking for modulation, changes in the signal that carry information, like how a radio broadcast has a carrier wave that gets modulated with the actual audio. And they'd be looking for deliberate targeting, a signal pointed at us specifically, or signals pointed at multiple stars. But here's what's interesting. As technology has advanced, we've realized there might be other ways to detect aliens. Technosignatures, they're called. Signs of alien technology. For example, a Dyson sphere, or more likely, a Dyson swarm. This is a hypothetical megastructure where a civilization builds a bunch of solar panels or habitats in orbit around their star, covering a large fraction of the star's energy output. If an alien civilization built something like that, we might be able to detect it because it would block some of the star's light from reaching us, or it would re-radiate that energy in the infrared. We've actually looked for Dyson swarms, searched for stars that are emitting unusual amounts of infrared radiation, which might indicate engineering on a megastructure scale. And we found nothing, though there was one star that was interesting, Tabby star, also called KIC 8462852. It has this weird dimming pattern. It gets brighter and dimmer in ways that don't match what we'd expect from planets. Some people speculated it could be a Dyson swarm under construction, and for a moment, everyone got excited. This could be it. This could be the evidence of alien engineering. But then, better observations came in, and the dimming seemed to be caused by dust, by a cloud of material orbiting the star, probably from asteroids that had collided. Totally mundane explanation. The excitement died down. Or maybe, and this is the speculative part, maybe the aliens just didn't want us to know. Maybe they're deliberately hiding, deliberately making their star look normal. Which brings us to an interesting question. If aliens exist, would they want to communicate with us? Let me introduce you to the dark forest theory. The dark forest theory comes from a Chinese science fiction trilogy called The Three-Body Problem, and it's based on a simple idea. The universe is like a dark forest. Every civilization is a hunter with a gun, trying to survive. And the key rule is this. If a civilization broadcasts its existence, it reveals its location. And any other civilization that detects that broadcast will know where it is. And that might be dangerous because space is vast. Resources might be limited. And if one civilization discovers another, they can't know for sure that the other civilization is friendly. So the rational choice might be to destroy them, to eliminate the competition. In the dark forest theory, broadcasting is essentially suicide. You're announcing your location to potentially hostile civilizations. So civilizations don't broadcast. They stay silent. They hide. This would explain the Fermi Paradox perfectly. The universe could be teeming with life, but all of that life has learned the same lesson. The cost of being found is too high. So everyone stays quiet. It's bleak, but it's logically sound. Now we haven't learned this lesson yet. We're still broadcasting. We're putting our civilization's location out there. The Arecibo message we sent in 1974 is on its way to M13. Our television signals and radio broadcasts are leaking into space. If the dark forest theory is correct, we're making a terrible mistake. I remember reading about this theory when I was in college, and I thought it was cool, but probably wrong. Surely civilizations would want to communicate. Surely there would be a benefit to exchanging information, to making alliances. But the more I've thought about it, the more I think it might be right. Because here's the thing, in a universe where any civilization could be a threat, where you can't trust anyone, the logical strategy is to hide. To develop your technology in secret. To not broadcast until you're so powerful that no one can threaten you. But if every civilization thinks this way, then everyone stays silent. Forever. It's a prisoner's dilemma on a cosmic scale. The rational individual choice, silence, leads to the worst collective outcome, complete isolation. This might be why we haven't found aliens yet. Not because they don't exist, but because they're hiding. Let me tell you about a project I worked on in graduate school. I did my PhD in astrophysics, studying exoplanet atmospheres, specifically looking for biosignatures, signs of life in the atmosphere of distant planets. The idea is simple. On Earth, our atmosphere is out of chemical equilibrium. It's full of oxygen, 21% of the air we breathe. But oxygen is reactive. It combines with other elements. In the absence of life, all the oxygen would disappear from the atmosphere in a few million years. The fact that Earth's atmosphere has oxygen is because life is constantly producing it. Photosynthetic organisms, plants and algae, produce oxygen as a waste product. So if an alien planet has oxygen in its atmosphere, that's a sign of life. That's a biosignature. We can measure exoplanet atmospheres by looking at what happens when they transit in front of their star. The starlight passes through the planet's atmosphere, and different molecules absorb different wavelengths of light. So by analyzing the light, we can figure out what's in the atmosphere. With the James Webb Space Telescope, we've gotten good enough at this that we can actually detect biosignatures in exoplanet atmospheres. We can look for oxygen, for methane, for other gases that might indicate life. And we've started analyzing the atmospheres of some potentially habitable exoplanets. And so far, we've found nothing. No oxygen, no methane, no obvious signs of life. Now, this doesn't mean there's no life on those planets. It could mean that life exists, but it's not photosynthetic. It could mean that the life is microbial, not producing large amounts of gas. It could mean that the life is there, but in a very different form than anything on Earth. But it does mean that life is not everywhere. It's not obvious. It's not jumping out at us, which supports the rare Earth hypothesis, which supports the idea that life is less common than we thought. I remember the day I was analyzing data from one of these observations. It was a planet called K218b. It's about 2.6 times the size of Earth, orbiting in the habitable zone of a red dwarf star. And we detected water vapor in its atmosphere. Water vapor in the atmosphere of an exoplanet. It was huge news. And I was analyzing the spectrum, looking for other gases, and I remember thinking, this could be it. This could be the planet where we find evidence of life. And then I looked at the full spectrum, and there was no oxygen, no methane, no biosignatures, just water, which is interesting, but not a sign of life. I spent weeks analyzing that data, looking for something I might have missed, some signal that could indicate microbial life. And I found nothing. It was disappointing. But it was also clarifying, because it made me realize that even if we had the perfect instruments, even if we could detect biosignatures, we might not find any, because life might just be rare. That was when I started to really internalize the silence, not as a mystery to be solved, but as a fact to be accepted. The universe might just be mostly empty, mostly devoid of life. And we might be one of the few places where thinking things evolved. Okay, let's talk about what happens if we do find something. What if tomorrow SETI picks up a signal, a clear, unmistakable signal from an alien civilization? What happens then? First, there would be confirmation. Scientists would verify the signal. They'd make sure it wasn't a hoax, wasn't interference, wasn't a natural phenomenon. This would probably take days or weeks. Then it would leak. Someone would tell someone, and word would spread. The media would pick it up. It would be the biggest news story in human history. Within hours, it would be known worldwide. Governments would be meeting. Religious leaders would be making statements. Scientists would be trying to figure out what to do next. And then, what? Here's where it gets complicated because we don't actually have a protocol for this. I mean, we do have SETI's post-detection protocol. It's a set of guidelines that scientists agreed to follow if a signal is detected, but it's not legally binding. It's not enforceable. It's just a gentleman's agreement. And one of the key points in the protocol is don't respond, don't send a message back, wait for consensus. Make sure everyone understands what we're doing before we start broadcasting our location to the cosmos. But will countries actually follow that? Will China wait for international consensus? Will the United States? Will Russia? Probably not. I think within days of detecting a signal, some country would be sending a response, trying to establish communication, trying to be the first civilization to make contact. And the dark forest implications of that are significant. If the aliens have been waiting to see if any civilization would respond to a signal, a response would confirm that we're here, that we're intelligent, that we're worth paying attention to. And we wouldn't know if that's a good thing or a bad thing until it's too late. I've thought about this a lot. What I would do if I detected a signal, and I think I would respond. I think the benefits of communication would outweigh the risks. But that's easy for me to say. I'm not the one making the decision for all of humanity. Let me take a step back. Let me tell you about something we actually know we can do to detect aliens. In the 1960s, an astronomer named Jill Tarter started working on SETI. She spent her entire career listening to the stars, searching for signals, and she didn't find any, but she developed methods, techniques. She helped establish protocols for what a signal would look like if we ever found one. She also developed the idea of technosignatures, signs of technology that aren't necessarily radio signals. For example, a laser signal. Aliens could send messages using powerful lasers, beaming them across space. We could potentially detect these with the right equipment. Or they could send signals using gravitational waves. We just recently developed the technology to detect gravitational waves. And gravitational waves could carry information just like radio waves can. Or they could build megastructures that we could see, Dyson spheres, as I mentioned, or orbital habitats, or space elevators, or something we haven't even thought of yet. The point is, there are multiple ways to look for aliens, and we're getting better at looking all the time. Jill Tarter eventually retired from full-time research, but her work laid the foundation for decades of searching, and she's still involved in SETI, still thinking about how we can improve our search. When I was in graduate school, I met her once at a conference. I told her how her work had inspired me to get into this field. And she said something I'll never forget. She said, "The universe is a big place, and we've only started looking. We're like people on a beach at night asking if there's anyone else on the beach. We've called out a few times, but we're still in the first moments of searching. The universe is dark, and we've just turned on a flashlight." That image stuck with me. A flashlight on a beach, calling out into the darkness. And maybe that's all we can do. Maybe that's all we should do. Now let me tell you about something that keeps scientists awake at night. Something that might actually explain the Fermi Paradox better than any of the theories I've mentioned so far. What if the great filter is in the future? What if civilizations regularly develop to the point where they can broadcast, but then something happens, something that prevents them from ever being heard? For example, what if life goes digital? Imagine a civilization that develops artificial intelligence, real, genuine intelligence, not just tools, but actual thinking machines. and then they upload their minds into those machines. They transition from biological beings to digital beings. Digital beings don't need to leave radio signals. They don't need to broadcast into space. All of their communication could happen internally through networks, through quantum entanglement, or whatever advanced communication method they've developed. They'd be completely invisible to our current detection methods. And this might be common. Maybe most civilizations that reach the technological level to broadcast end up developing digital intelligence and uploading their minds. And once they do that, they go silent. Or maybe they move on to other forms of existence that we can't even conceive of. Or maybe they harness so much energy that they become invisible to us. They shift so much of the universe's radiation into their own internal computations that there's nothing left to detect from the outside. These are speculative ideas, but they point to something important. Our understanding of intelligence and civilization is based on human experience, and human experience might be an anomaly. There might be forms of intelligence that don't need radio broadcasts, forms of civilization that don't leave the kinds of traces we're looking for, which means we could be surrounded by aliens and never know it. We could have passed through alien megastructures without seeing them. We could be orbiting around stars that are being engineered by civilizations we have no way to detect. The silence might not mean we're alone. The silence might just mean we don't know how to listen. All right, I want to bring this back to Earth, back to us. Because the real question isn't really about aliens at all. The real question is about us. Why haven't we found aliens yet? That's what we've been asking. But maybe the better question is, what does that silence tell us about our own future? If the great filter is ahead of us, then we're in trouble. We're going to face something that destroys civilizations. And we don't know what it is. We don't know when it's coming. We don't know if we can survive it. That's a terrifying thought. But it's also clarifying. Because if that's true, then right now, this moment in history is incredibly important. Because this might be the moment where our civilization either survives or doesn't. This might be the moment where we choose to grow up, to become serious about our future, or where we keep sleepwalking toward catastrophe. The Fermi Paradox is sometimes called the Great Silence, and I think that's appropriate, because it's not just silence from the cosmos, it's a silence that echoes back to us. It's the silence of a universe that doesn't care about us, that doesn't validate us, that doesn't promise us safety. And in that silence, we have to decide what to do. We have to decide whether we're going to be a civilization that destroys itself through its own technology, or whether we're going to be a civilization that figures out how to survive, how to grow, how to eventually reach out into that silence and fill it with our own voice. Because here's the thing, if the silence is real, if we really are alone, or nearly alone, then that's not a reason to despair. That's a reason to act. Because if we're alone, then we're responsible. We're responsible for what happens to intelligence in this universe. We're responsible for whether consciousness survives. We're responsible for whether thinking things continue to exist. That's a huge responsibility. But it's also an amazing opportunity. Because if we survive, if we figure out how to get past the great filter, if we develop a civilization that's wise enough to survive its own technology, then we might spread out into space. We might explore the galaxy. We might encounter other civilizations, or we might seed life across worlds, becoming the aliens that some future civilization wonders about. And we'd break the silence. Let me tell you about a moment that gave me hope. I was doing research for my PhD, and I was reading about climate change, about how bad it could get, about sea level rise and ecosystem collapse and extinction rates. And I was getting depressed again because it seemed like we were failing, like we were sleepwalking toward catastrophe, unable to stop ourselves. But then I read about something called the Kigali Amendment. In 2016, nearly 200 countries agreed to phase out hydrofluorocarbons, chemicals that are used in refrigeration and air conditioning, but which damage the ozone layer. This was a big deal because it meant that governments, despite their disagreements, could actually agree to act on a global environmental problem, could actually implement policy to fix it. And you know what? It worked. The ozone layer is recovering. Scientists project that it will be fully healed by the year 2070. We fixed something. We identified a global problem, agreed to solve it, and did it. And that gave me hope because it meant that we're not incapable of acting. We're not helpless in the face of global catastrophe. We can choose to survive. That doesn't mean we will. It doesn't mean we'll get past all the filters, but it means we can. It means we have agency. We have the ability to choose our future. And that changes everything. Okay, so let's talk about what we're doing right now to search for aliens. The primary method is still radio SETI, pointing radio telescopes at the sky, listening for signals, but we're also doing something else. We're looking for technosignatures, laser signals, gravitational waves, unusual astronomical phenomena that might indicate engineering on a massive scale. And we're analyzing exoplanet atmospheres for biosignatures. And we're thinking about other ways we might detect aliens. One interesting idea is to look for Dyson swarms. But instead of looking for the infrared radiation they emit, we could look for the waste heat they produce. Because no energy conversion process is 100% efficient. So a civilization running a Dyson swarm would produce heat as a byproduct. And that heat would be detectable. Another idea is to look for megastructures in the form of stars that are moving in unusual ways. Because if a civilization is using a star's energy on a massive scale, they might be moving the star, redirecting it. And that would be detectable as an unusual proper motion through space. Another idea is to look for what's called astroengineering, large-scale modification of planetary systems, removing planets, rearranging orbits, terraforming worlds on a massive scale. All of this might be detectable if we knew what to look for. We're also starting to think about biosignatures beyond oxygen. What if alien life uses a different biochemistry? What if it produces different gases? We're expanding our search to look for things like phosphine or dimethyl sulfide or other molecules that might indicate life. And we're getting better at this. The James Webb Space Telescope has capabilities that were unimaginable just 20 years ago. And future telescopes, like the Extremely Large Telescope being built in Chile, or the next generation of space telescopes, they'll be even more powerful. So we're looking, we're really looking, and we're getting better at it every year. But so far, we're finding nothing, and I think that's important to sit with. We're not finding nothing because we're not looking hard enough. We're finding nothing because there might not be anything to find, or because what we're looking for isn't what we think it is. Let me talk about something that changed how I think about this whole question. I was at a conference a few years ago, and there was a talk by a researcher named Carl Sagan. Well, actually, Sagan had died long before I was born, but this was someone talking about Sagan's ideas. And they mentioned something Sagan said. Sagan was one of the biggest proponents of the idea that life is common in the universe. He believed in the numbers. He believed the Drake equation. He thought we'd find aliens. But he also said something else. He said that the universe might be full of life, but that life might be mostly simple, microbial, bacteria, and simple single-celled organisms. Because the jump from simple life to complex life is actually really hard. On Earth, simple life emerged maybe 3.5 billion years ago, but complex life, eukaryotes, cells with nuclei, didn't emerge until maybe 2 billion years ago. That's a billion-year gap. And multicellular life emerged even later. Animals didn't show up until about 600 million years ago. So even though life emerged quickly on Earth, it took a long time to get complex. And that suggests that complexity is the hard part. That simple life might be common, but complex life might be rare. Intelligent life would be even rarer. And civilizations, beings who develop technology, who can broadcast signals, might be incredibly rare. Sagan called this the principle of cosmic humility, the idea that we shouldn't assume we're special, but that we also shouldn't assume we're common. We should be humble about our place in the universe. And I think that's the right attitude. We don't know if we're alone. We don't know if we're one of billions. We don't know if intelligent life is common or rare. What we know is that we're here, that we exist, that we think, and that matters. Now I want to address something that a lot of people ask. If aliens exist, why haven't they visited us? This is called the Great Filter Problem, or sometimes the Fermi Paradox in its most literal form. If aliens are out there, why haven't they come here? The answers are interesting. First, space is really big, like incomprehensibly big. The nearest star system to us is Alpha Centauri, about 4.3 light years away. That's about 40 trillion kilometers. Our fastest spacecraft, Voyager 1, is traveling at about 17 kilometers per second. At that speed, it would take about 70,000 years to reach Alpha Centauri. So even if aliens exist in the next star system over, it would take them tens of thousands of years to get here, and they'd have to spend enormous resources to do it. Now, a sufficiently advanced civilization might be able to do this. They might develop faster than light travel, or suspended animation, or some other technology we haven't thought of. But there's no law of physics that requires faster than light travel to be possible. In fact, our current understanding suggests it's not possible. Relativity puts a speed limit on the universe, the speed of light. So even advanced aliens might not be able to reach us. Second, there's the question of detection. If aliens visited Earth, we'd probably notice. But would we? If they wanted to hide, they could hide. They could cloak their ships, or visit in deep space, or do their survey work without us knowing. Or maybe they have visited. Maybe there are alien probes in our solar system right now, observing us, waiting for us to reach a certain level of technological development before making contact. This is speculative, but it's possible. Third, there's the question of motivation. Why would aliens travel across the galaxy to reach Earth? What would we have that they want? If they're sufficiently advanced, they probably don't need our resources. They probably don't need us for anything. Maybe they're just studying us, like we study bacteria under a microscope, in which case they'd be here, but hidden, observing us without our knowledge. Or maybe they're not interested in us at all. Maybe Earth is just one among billions of inhabited worlds, and we're not special enough to warrant a visit. All of these possibilities are consistent with what we observe. No confirmed alien visitors. So the lack of visits doesn't necessarily mean aliens don't exist. It just means that either aliens don't exist, or they haven't reached us, or they've chosen not to contact us. All right, I want to zoom out for a moment. I want to talk about what all of this means. For most of human history, we thought we were the center of the universe. We thought God created the world for us. We thought we were special. Then Copernicus said the Earth wasn't at the center of the solar system. Then we realized the sun wasn't at the center of the galaxy. Then we realized our galaxy was just one of billions. And with each realization, we became smaller. Our cosmic significance diminished. The Fermi Paradox is the final insult, because it suggests that not only are we not at the center of the universe, we might also be alone, or nearly alone. We might be one of the only thinking things in the cosmos. That sounds depressing. It sounds like the final blow to human significance. But I've come to see it differently. Because if we are alone, or nearly alone, then we're incredibly significant. Because we're the only chance for intelligence to continue. We're the only voice in the silence. That's not nothing, that's everything. And if we're not alone, if other civilizations exist out there, then we need to survive long enough to make contact with them, to join the community of intelligent beings, to take our place in the galaxy. Either way, the implication is the same. We need to survive. We need to grow up as a species. We need to become the kind of civilization that can get past the great filter. Let me tell you what I think the great filter is. This is my hypothesis based on everything I've learned. I think the great filter is not a single thing. I think it's a series of filters, a gauntlet that every civilization has to run. The first filter is the emergence of life itself. Life might be rare. It might require very specific conditions. Most planets might be sterile. The second filter is the emergence of complexity. Simple life might be common, but complex life is harder. It took 1 billion years on Earth. The third filter is intelligence. Intelligence might be rare. It might require specific evolutionary pressures, specific environmental conditions. The fourth filter is language and civilization. True language, true culture, true technology. That might be rare. And then if you make it past all of those, you have to survive the technological gauntlet. Nuclear weapons, climate change, artificial intelligence, nanotechnology, whatever comes next. And most civilizations probably fail at some point in that gauntlet. Now the question is, where in this gauntlet are we? We've clearly made it past the first few filters. Life exists, complexity exists, intelligence exists, civilization exists, but we're in the technological gauntlet right now. We're facing existential risks, climate change, nuclear weapons, AI, synthetic biology. We might not make it through, but we might. We have the knowledge, we have the tools, we have the ability to survive. We just have to choose to. And if we do survive, if we make it through this gauntlet, then we'll be one of the few civilizations that ever make it this far. We'll be rare, we'll be special, and we'll break the silence. Okay, I want to end this with something personal, because this whole investigation, this whole question about why we haven't found aliens yet, it's become deeply personal for me. I've spent the last decade of my life studying this, thinking about it, losing sleep over it. And I've realized that the question isn't really about aliens at all. The question is, what does it mean to be alive? What does it mean to think? What does it mean to exist in a universe that might not care about you? And the answer, I think, is this. It means everything. Because meaning isn't something that's given to you by the universe. Meaning is something you create in the finite time you have. With the finite resources available to you, the fact that we might be alone doesn't diminish that. The fact that no one might be watching doesn't matter. We're here. We exist. We think. And that's enough. But more than that, we have the opportunity to make sure that thinking continues. We have the opportunity to build a civilization that survives, that grows, that spreads. We have the opportunity to break the silence, not by receiving a signal from the stars, but by becoming the signal ourselves, by becoming the kind of civilization that broadcasts light into the darkness, that says, we were here, we thought, we mattered. That's what drives me now. Not the search for aliens, but the determination to make sure that humanity survives long enough to matter. Because if we do, if we make it through the technological gauntlet and into a post-scarcity civilization that's wise enough not to destroy itself, then maybe we'll spread out into the stars. Maybe we'll visit other worlds. Maybe we'll encounter other civilizations. And maybe, just maybe, we'll finally break the silence. Or maybe we'll remain alone. Maybe we'll be the only thinking things in this vast cosmos. But that doesn't change what we need to do. We need to survive. We need to grow. We need to build a civilization worth preserving. Because if we don't, if we destroy ourselves through our own technology or our own negligence, then the silence will remain. The universe will remain empty of intelligent thought. And the greatest tragedy of all won't be that we were alone. It will be that we had the chance to change that and we squandered it. So that's my answer to the question my dad couldn't answer when I was 12 years old, lying in that field, staring up at the stars. Why haven't we found aliens yet? We haven't found them yet because they might be rare, because the conditions for intelligent life to emerge, and for that life to develop civilization, and for that civilization to survive its own technology, those conditions might be incredibly stringent. We haven't found them because they might be hiding, using the dark forest strategy, staying silent because they know that broadcasting is dangerous. We haven't found them because they might have already come and gone, because every civilization might eventually destroy itself through the technologies it creates, because the universe might be full of ruins. Or we haven't found them because we don't know how to listen, because they might have evolved into forms of existence we can't detect, because they might be so far away that our signals haven't reached them yet. Or, and this is the possibility that keeps me awake at night, we haven't found them because we're the first, because we're the earliest intelligent civilization in this corner of the galaxy, because we're the ones who are going to break the silence. And if that's true, then the responsibility is on us. We have to survive. We have to build a civilization that lasts. We have to reach out into the stars and fill the silence with life. Because if we don't, no one else will. That's what the silence means to me. Not a verdict on our worth, not a confirmation that we're alone and worthless. A challenge, a call to action. We need to grow up. We need to become wise. We need to figure out how to survive. Because we might be humanity's only chance. I was 12 years old when I first asked the question that would define my life. I was lying in a field outside my hometown, somewhere in rural Illinois. It was summer, late July, and the stars were out in a way that stars only are when you're far from the city lights. The Milky Way stretched across the sky like a river of diamonds. My dad had brought me out there to show me Saturn through his telescope. We'd set it up on a tripod, and I'd pressed my eye against the eyepiece and seen the rings for the first time. I remember the shock of it, the reality of it, that those rings were real, that they existed, that we could see them from Earth. After we packed up the telescope, we lay on our backs in the grass, just looking up. And after a while, I asked him a question. Dad, are we alone? He knew what I meant. Not alone in the field, alone in the universe. Are there other people out there? Other civilizations? Other beings looking up at the stars? And he couldn't answer me. He said, I don't know, buddy. I don't know. I remember feeling frustrated by that answer. Not because he didn't know, I understood that, but because he didn't seem to think it was an important question. He seemed to think it was okay to not know. It wasn't okay with me. I wanted to know. I wanted to understand if we were alone. And I spent the next 20 years trying to answer that question. When I got to college, I learned that I wasn't the only one asking this question. There was a whole field of study dedicated to it. Astrobiology, the search for extraterrestrial life. And there was a paradox, the Fermi Paradox. It goes like this. The universe is big, really big. There are an estimated 100 billion galaxies in the observable universe. Each galaxy has an estimated 100 billion stars. That's 10 to the 24th power stars. A septillion stars. Many of these stars have planets. We know this because we've discovered thousands of exoplanets, and the evidence suggests that most stars have planets. And many of these planets are probably habitable. They're in the habitable zone around their star, far enough away that they're not too hot, close enough that they're not too cold. They could have liquid water. They could have life. If even a tiny fraction of these planets develop life, there should be billions of civilizations out there. And if even a tiny fraction of those civilizations develop radio technology, they should be broadcasting signals. We should be able to hear them. But we don't hear anything. We listen to the stars, and we hear nothing but silence. This is the paradox. The numbers suggest the universe should be teeming with life, but observation suggests it's silent. So where is everybody? That was the question that physicist Enrico Fermi asked at lunch one day in 1950. And it's the question that has haunted scientists ever since. To understand the Fermi paradox, you need to understand the Drake equation. In 1961, Frank Drake created a mathematical formula to estimate the number of communicative civilizations in our galaxy. It is the product of these factors. R star equals the rate of star formation. Fp equals the fraction of stars with planets. NEOE equals the number of habitable planets per star. FL equals the fraction of habitable planets that develop life. Fi equals the fraction of life. Bearing planets that develop intelligent life. Fc equals the fraction of intelligent civilizations that develop technology. L equals the length of time a civilization lasts before destroying itself. This equation seems straightforward. But the problem is we don't actually know most of these values. We know R star. We've measured star formation rates pretty well. About 10 billion stars form per year in the Milky Way galaxy. We're starting to know Fp and Ne thanks to the Kepler Space Telescope and other surveys. We've learned that most stars have planets, and a significant fraction of those planets are in the habitable zone. So Fp is probably around 1, maybe even higher, and Ne is probably somewhere between 0.1 and 1. But Fl, the fraction of habitable planets that develop life, we have no idea. We have one data point, Earth, and Earth developed life. So either Fl is 1, life develops on all habitable planets, or it's something much lower, life is rare, and we just happen to be lucky. Same with Fi. We have one data point, Earth developed intelligent life. So either intelligent life is common or we're incredibly lucky. And FC and L, the fraction of civilizations that develop technology and how long they last, we have no idea about those either. So the Drake equation is useful as a framework for thinking about the problem, but without real data, it's basically useless for calculating actual numbers. Different scientists plug in different values and get wildly different results. Optimistic estimates, billions of civilizations in the galaxy. Pessimistic estimates, we might be alone. And depending on which estimate you believe, you get different answers to the Fermi Paradox. What strikes me most about the Fermi Paradox is the silence. We've been broadcasting radio signals for about 100 years. Our television signals, our radio broadcasts, our radar, they all leak into space. They're like a beacon saying, we're here, we're here, we're here. And we've been listening for about 60 years. The search for extraterrestrial intelligence, SETI, has been pointing radio telescopes at the sky, listening for signals from aliens. And in all that time, we've heard nothing. No signals, no messages, no beeping sounds in the night, just silence. You might think that silence is just silence, the absence of a signal. But scientists have a different way of looking at it. Silence is information. If the universe was full of radio broadcasting civilizations, we should have detected at least one. We've searched through billions of radio frequencies. We've pointed telescopes at thousands of stars. We've been listening for decades, but we've found nothing. This suggests one of several possibilities. Life is rare. It doesn't emerge often. Intelligence is rare. Life emerges, but usually stays simple. Civilizations are rare. Intelligence emerges, but usually doesn't develop technology. Civilizations don't last long. They develop technology, but then destroy themselves. Civilizations develop technology, but don't broadcast radio signals. All of the above. There are multiple filters. Each of these possibilities has profound implications. Before we can talk about how common life is, we need to understand what makes a planet habitable. For most of human history, we thought the conditions for life were pretty broad. Life is tough. It can survive almost anywhere. But as we've learned more, we've realized that the conditions for complex life to emerge are actually quite specific. Let me walk you through them. The habitable zone. First, there's the habitable zone. This is the region around a star where a planet can have liquid water on its surface. Not too hot, where water evaporates into the atmosphere. Not too cold, where water freezes into ice, but just right. For a star like our Sun, the habitable zone is roughly the region between the orbits of Venus and Mars. Earth is right in the middle of it. But the habitable zone isn't fixed. It depends on the star. A hot star has a habitable zone farther away. A cool star has a habitable zone closer in. And even if a planet is in the habitable zone, that doesn't guarantee it's habitable. It just means it's possible for it to have liquid water, because there are other factors. Atmospheric composition. A planet needs an atmosphere to maintain liquid water. An atmosphere traps heat through the greenhouse effect. Without an atmosphere, water would evaporate or freeze. But the atmosphere also needs to be the right composition. Too much greenhouse gas, and the planet becomes a Venus-like hellscape, with temperatures hot enough to melt lead. Too little, and the planet becomes a frozen ball. Earth's atmosphere is about 21% oxygen, 78% nitrogen, and 1% argon and other gases. This composition is maintained by life itself. Photosynthetic organisms produce oxygen. Denitrifying bacteria cycle nitrogen. Without life, Earth's atmosphere would be completely different. Might not be able to maintain liquid water, so the atmosphere itself is dependent on the presence of life. This creates a chicken and egg problem. You need liquid water to have an atmosphere that sustains liquid water. The answer seems to be that life emerges in the oceans, where water is already present and stable. And then life gradually changes the atmosphere to make it more habitable. Magnetic field. This is something I mentioned briefly before, but it's important. A planet needs a magnetic field to protect it from solar radiation. The sun constantly emits a stream of charged particles called the solar wind. This wind would strip away an atmosphere if the planet didn't have a magnetic field to deflect it. Earth has a strong magnetic field because we have a molten iron core that's rotating. The movement of liquid iron generates electrical currents which create the magnetic field. But not all planets have this. Venus and Mars don't have strong magnetic fields, and as a result, their atmospheres have been stripped away by the solar wind. Mars probably had a thicker atmosphere in the past. It might have been warm enough for liquid water, but without a magnetic field, the solar wind gradually removed the atmosphere, and Mars became a cold, dry desert. So a habitable planet needs a magnetic field, and that requires a molten core, which requires the planet to be large enough and young enough to still have heat from its formation. Plate tectonics, I mentioned this before too. Plate tectonics is the process where the crust of a planet is broken into several plates that move around. On Earth, the plates collide, creating mountains. They separate, creating rift valleys and new crust. They slide past each other, creating earthquakes. This process seems destructive, and in a sense, it is. It creates earthquakes and volcanoes and geological disasters. But it also does something crucial. It recycles carbon. Here's how it works. Carbon dioxide in the atmosphere combines with rainwater to form a weak acid. This acid dissolves rocks, including silicate rocks, which contain silicon and oxygen. The dissolved silicates get carried by rivers to the ocean. In the ocean, the silicates combine with calcium to form calcium silicate. This sediment gets buried on the ocean floor. Over time, the sediment gets pushed down into the mantle through subduction, where one tectonic plate gets pushed under another. And in the mantle, the heat and pressure break down the calcium silicate, releasing carbon dioxide, which bubbles back up to the surface through volcanoes. This is called the carbonate silicate cycle, and it's crucial because it regulates atmospheric carbon dioxide levels. If carbon dioxide levels get too high, the greenhouse effect makes the planet hotter. Higher temperatures mean more rain, which removes more carbon dioxide from the atmosphere, which cools the planet. If carbon dioxide levels get too low, the greenhouse effect weakens. The planet gets colder. Colder temperatures mean less rain, which means less carbon dioxide is removed. Carbon dioxide builds up, warming the planet. It's a feedback loop that keeps atmospheric CO2 in a habitable range. Without plate tectonics, this regulation wouldn't happen. Carbon dioxide would either accumulate or be depleted, and the planet would become uninhabitable. Venus might have had plate tectonics once, but it lost them. And without plate tectonics to regulate carbon dioxide, the greenhouse effect got stronger and stronger. The planet got hotter and hotter, and all the water evaporated. Size and age. A planet also needs to be the right size and age. If a planet is too small, it cools too quickly. The core solidifies. The magnetic field disappears. The planet becomes geologically dead. If a planet is too large, the pressure and heat from the mass cause it to become a gas giant. Earth is right in the middle, about one Earth mass, and the planet needs to be young enough to still have a hot core for the magnetic field and plate tectonics, but old enough for life to have time to evolve, at least a few billion years. Earth is about 4.5 billion years old. We've had stable conditions for complex life to evolve for maybe 600 million years. That's a long time, but it's required for intelligence to develop. Stellar stability. The star itself also matters. A star needs to be stable. It needs to maintain roughly the same luminosity for billions of years. Stars like our sun are stable for about 10 billion years. They spend most of that time on the main sequence where they're fusing hydrogen into helium and producing steady energy output. But some stars are unstable. They vary in brightness. They produce intense flares of radiation. They're not good hosts for habitable planets. Red dwarf stars, the most common type of star, are stable, but they're very dim. Their habitable zones are close to the star, which means planets in their habitable zones are tidally locked. One side always faces the star. One side always faces away. This creates extreme temperature differences and might prevent the development of complex life. Also, red dwarf stars can produce powerful flares that could strip away a planet's atmosphere and sterilize its surface. So not all stars are equally good hosts for habitable planets. The late heavy bombardment. There's one more factor I want to mention. The solar system went through a period called the late heavy bombardment, where a massive number of asteroids collided with the inner planets. This happened about 4 billion years ago. Asteroids bombarded Earth, vaporizing the oceans and sterilizing the surface. But this bombardment might have been crucial for life, because the asteroids brought water and organic compounds to Earth. They might have been essential for the origin of life. Every solar system probably goes through something similar, and in most cases, the bombardment is probably destructive. It probably prevents life from emerging. But occasionally, a planet survives the bombardment and develops life. All of these factors, the habitable zone, the atmosphere, the magnetic field, plate tectonics, stellar stability, the right size, and age, they have to all come together. And if even one is missing, the planet probably can't support complex life. This is the basis of the rare Earth hypothesis. Proposed by paleontologist Peter Ward and astronomer Donald Brownlee in 2000, the rare Earth hypothesis suggests that habitable planets are much rarer than the Drake equation would suggest. Not because planets are rare. We now know planets are common, but because habitable planets are rare, because the conditions have to be just right. Let me walk through the numbers. We estimate there are about 200 billion planets in the observable universe. That's 2 times 10 to the 24th power planets. Of those, maybe 10 to 20% are in the habitable zone of their star. That's about 4 times 10 to the 23rd power potentially habitable planets. But how many of those actually have the right conditions? How many have a magnetic field? How many have plate tectonics? How many are the right size? How many orbit the right kind of star? If we apply the rare Earth factors, we can reduce the number significantly. Let's say only 10% of planets in the habitable zone have all the right conditions. That's 4 times 10 to the 22nd power planets. Or maybe it's 1%. That's 4 times 10 to the 21st power. Or maybe it's 0.1%. That's 4 times 10 to the 20th power. We don't know. But the rare Earth hypothesis suggests that the number is much smaller than the optimistic estimates in the Drake equation. And if habitable planets are rare, then life might be rare too, and intelligence might be even rarer, which could explain the silence. But wait, even if a planet is habitable, that doesn't mean life will emerge. Life requires very specific conditions, and the origin of life, abiogenesis, is still a mystery. We don't fully understand how life began on Earth. We have some ideas, some hypotheses, but no definitive answers. Here's what we think happened. About 3.8 to 4 billion years ago, Earth had a different atmosphere. It was probably dominated by nitrogen, carbon dioxide, methane, and ammonia. No free oxygen. We don't know exactly what the surface was like. It might have been warm and wet, or it might have been cold and icy. Scientists debate this, but somehow in this primordial environment, chemical reactions began to occur that created organic molecules. Amino acids, nucleotides, the building blocks of life. We've done experiments that show how this could happen. In 1952, Stanley Miller and Harold Urey created an experiment where they simulated the primordial atmosphere, added water, and ran electricity through it, simulating lightning. After a few days, they found amino acids in the solution. This showed that organic molecules could form spontaneously from simple chemical ingredients. Since then, scientists have found similar processes could create organic molecules from other combinations of chemicals. Sunlight, heat, radioactive decay, and many other energy sources could drive these reactions. So the formation of organic molecules seems plausible. But how did these molecules organize into life? How did they form self-replicating systems? How did they develop into cells? This is where the mystery deepens. One hypothesis is the RNA world hypothesis. This suggests that early life was based on RNA, a molecule similar to DNA, but more versatile. RNA can both store information, like DNA, and catalyze reactions, like proteins. In this hypothesis, RNA molecules begin to self-replicate. Some RNA molecules are more efficient at replicating than others, so they're selected for. Over time, these RNA molecules become better and better at replicating. Eventually, proteins evolve to help with replication. DNA evolves as a more stable storage molecule, and cells evolve as containers for these molecules. But this is still speculative. We haven't been able to create a self-replicating RNA system in the lab. We don't fully understand how it would happen. Another hypothesis is that life began at hydrothermal vents on the ocean floor. These vents are hot, mineral-rich environments where chemical gradients could drive reactions. Some scientists think life might have emerged in these vents, in natural pores in the rocks that serve as primitive cells. But again, this is speculative. The point is, we don't understand the origin of life. And that's a huge gap in our knowledge. Because if we don't understand how life began, we can't estimate how often it happens. We can't fill in the FL parameter of the Drake equation. It could be that life begins very easily. Almost every habitable planet develops life, in which case life is common. Or it could be that life is incredibly hard to start. Maybe Earth got incredibly lucky. Maybe life only emerges on 1 in a billion habitable planets, in which case life is rare, and the silence makes sense. Let's assume life does emerge on habitable planets. What happens next? On Earth, life emerged relatively quickly. We find evidence of simple, single-celled life, bacteria-like organisms, about 3.5 billion years ago, maybe even earlier. So if the question is, How often does simple life emerge? The answer seems to be pretty often, or at least it happened on Earth. But then something strange happens. Simple life dominates Earth for about 1 billion years. And then nothing. For 1 billion years, Earth is just bacteria. Then, about 2 billion years ago, complex life emerges. Eukaryotes, cells with nuclei and organelles. And it takes another 1.5 billion years before multicellular life emerges, about 600 million years ago. And then, after multicellular life exists, it still takes another 600 million years before intelligent life emerges. And even then, intelligent life had to evolve in a very specific way, under very specific conditions. So here's the pattern. Simple life emerges quickly, probably common. Complex life takes a long time, maybe rare. Intelligent life takes even longer, maybe very rare. This is what I call the complexity paradox. The more complex the life, the longer it takes to evolve, and the rarer it probably is. Let me explain why this might be the case. The jump from simple life to complex life is actually really hard. It requires a lot of evolutionary innovation. The eukaryotic cell is vastly more complex than the prokaryotic cell. It has a nucleus, mitochondria, endoplasmic reticulum, Golgi apparatus, all these specialized organelles. Where did these come from? The endosymbiotic theory suggests that some of these organelles came from other cells that were engulfed and incorporated. A large prokaryotic cell engulfed a smaller one, and instead of digesting it, the cell kept it. And the smaller cell became an organelle. This would require a lot of lucky events. The right cells colliding, the right conditions for symbiosis, and it might not happen very often. In fact, the jump to complex life might be so difficult that it only happened once on Earth. We have one origin of complex life. All complex life on Earth, all plants, animals, fungi, descended from a single eukaryotic ancestor. If it only happened once on Earth, how often does it happen on other planets? Maybe it's incredibly rare. Similarly, the evolution of intelligence is difficult and requires specific evolutionary pressures. On Earth, primates evolved large brains. But why? What was the evolutionary advantage? One hypothesis is that larger brains helped with social cooperation. Larger brains allowed for more complex social hierarchies, more strategic thinking, better communication. But social cooperation doesn't require intelligence. Ants are incredibly social, but they're not intelligent. So why did intelligence evolve in some lineages and not others? We don't fully understand it, and that suggests it might be rare. It might be an evolutionary dead end, a solution to a problem that only a few species face. So the complexity paradox suggests that while simple life might be common, intelligent life is rare. And that could explain the silence. The idea of a great filter was proposed by astronomer Robin Hansen in 1996. It's a way of thinking about the Fermi Paradox. The great filter is a step in the emergence of intelligent civilizations that is so difficult, so unlikely that it's rare. Maybe it's so rare that only a handful of civilizations in the entire observable universe ever get past it. There are two possibilities for where the great filter is. Behind us. The great filter is in the past. It's a step that's so difficult that it's rare for a civilization to reach where we are now. If this is true, then we should expect to find a lot of simple life in the universe. But intelligent civilizations should be incredibly rare. Ahead of us. The great filter is in the future. It's a step that intelligent civilizations usually fail. Once a civilization reaches a certain level, of development, something usually destroys it. If this is true, then intelligent civilizations might be somewhat common, but they usually don't last long. They usually destroy themselves. The question of which it is affects how we should view the future. If the great filter is behind us, we're incredibly lucky. We've made it through something almost impossible, and we should feel special. We should also feel like the universe is ours to explore. Because if we survive the great filter, we're probably capable of surviving whatever comes next. If the great filter is ahead of us, we're in trouble. We've made it to a certain point, but something is coming that will probably destroy us. And we need to figure out what it is and how to survive it. My hypothesis, based on everything I've learned, is that the great filter is somewhere in the middle. It's not a single thing. It's a series of filters. And we're somewhere in the middle of running the gauntlet. Let me walk through the filters I think exist. The first filter is the emergence of life itself. This is probably not the great filter, because we know life emerges. We're proof of it. But life might be rarer than we think. It might require very specific conditions. It might take a very long time to start. It might be rare enough that even though there are billions of habitable planets in the observable universe, only a fraction of them develop life. Let's estimate. If habitable planets are common, say there's 1 in every 10 star systems, and there are 200 billion stars in our galaxy, that's 20 billion habitable planets in our galaxy alone. If life emerges on 10% of habitable planets, that's 2 billion planets with life in our galaxy. But if life only emerges on 0.1% of habitable planets, that's 20 million planets with life. And if life only emerges on 0.01% of habitable planets, that's 200,000 planets with life. We don't know which is correct, but the emergence of life is clearly a filter. It's a step where many planets fail. The filter of complexity. The second filter is the emergence of complex life. This is a bigger filter than the emergence of life, because simple life probably emerges on most life-bearing planets. But complex life is rarer. On Earth, simple life emerged about 3.5 billion years ago, but complex life didn't emerge until about 2 billion years ago. That's a billion-year wait. And multicellular life didn't emerge until about 600 million years ago. Another 1.4 billion year wait. So the jump from simple to complex is hard. It takes a long time. And it might not happen on most planets. Why is it so hard? One reason is that simple life is stable. Bacteria have been around for 3.5 billion years, and they're still here. They've conquered almost every environment on Earth. They're incredibly successful. So once simple life emerges, it might stay simple. There's no pressure to become complex. Complex life only emerges if there's an advantage to being complex, and that advantage only exists under certain conditions. On Earth, one of those conditions was the oxygenation of the atmosphere. For about 2 billion years, Earth's atmosphere had almost no oxygen. It was reducing, not oxidizing. But then photosynthetic bacteria evolved, and they started producing oxygen as a waste product. Oxygen is actually toxic to simple cells. It damages their DNA. So the rise of oxygen, what's called the Great Oxidation Event, probably killed off a lot of simple life. But it also created an opportunity, because oxygen can be used for energy more efficiently than anaerobic processes. Cells that could use oxygen could get more energy from their food, and this energy could be used to power complex structures, complex cells with organelles, multicellular organisms, nervous systems, brains. So the great oxidation event might have been necessary for complex life to evolve. And the great oxidation event required photosynthetic life to evolve first. And that took billions of years. So the filter of complexity might be very strong. It might require very specific conditions. It might require the right kind of chemical evolution in the biosphere, and it might be rare. The third filter is the emergence of intelligence. This is probably the strongest filter we've found so far, because we have only one example of intelligence on Earth, and it took 3.5 billion years to evolve. In that time, there have been millions of species on Earth, but only one, humans, developed true language, true culture, true technology. Dolphins are intelligent, but they don't have technology. They don't have writing. They don't have cities. Elephants are intelligent, but same thing. Crows are intelligent. Octopuses are intelligent. Great apes are intelligent. But none of them develop civilization. Why is intelligence so rare? Why did it only emerge once? One hypothesis is that intelligence is metabolically expensive. A big brain requires a lot of energy. On Earth, we spend about 20% of our energy budget on our brains. That's a huge cost. For most animals, that cost isn't worth it. It's better to be fast or strong or have good senses. Intelligence only became advantageous in specific conditions. For primates, those conditions included living in social groups, where intelligence helps with social coordination, living in complex environments, where intelligence helps with navigation and problem solving, and having hands that could manipulate objects, allowing for tool use, which rewards intelligence. But these conditions are rare. Most species don't have all of them, so intelligence might be incredibly rare. It might be an evolutionary dead end, a solution to a specific problem that only a few species face. If that's true, then intelligent life might be very uncommon in the universe. Another hypothesis is that even when intelligence emerges, it doesn't always lead to technology. Intelligence is useful for survival, but technology requires a specific type of intelligence. It requires the ability to think abstractly, to imagine things that don't exist yet, to plan for the future, and it requires the right environment. Tool making requires hands, or tentacles, or something manipulative. It requires materials suitable for tools. It requires a social structure that values innovation. These conditions might be rare, so the filter of intelligence might be very strong. It might reduce the number of intelligent species in the universe by orders of magnitude. The fourth filter is the emergence of civilization and technology. Intelligence is necessary for civilization, but it's not sufficient. On Earth, modern humans evolved about 300,000 years ago, but civilization, cities, writing, organized government didn't emerge until about 10,000 years ago. That's a 290,000 year gap. For most of that time, humans were hunter-gatherers. They had language and culture and tools, but they didn't have civilization. What changed 10,000 years ago? The most popular hypothesis is agriculture. Humans learned to farm, and farming created surplus food. And surplus food allowed people to specialize. Some people could be farmers, some could be craftspeople, some could be leaders. And specialized roles led to more complex society, which led to government, which led to writing, which led to science and technology. But agriculture wasn't inevitable. For thousands of years after the development of agriculture, most human societies didn't adopt it. Some continued to be hunter-gatherers, and they did fine. Agriculture was actually hard. Early farmers worked harder, ate less well, and had worse health than hunter-gatherers. It took thousands of years before the benefits of agriculture outweighed the costs. So civilization might not emerge on every planet with intelligent life. It might require specific conditions, the right plants and animals to domesticate, the right geography, the right social structure. These conditions might be rare. So the filter of civilization might be strong. It might reduce the number of technological civilizations in the universe. And then once a civilization develops technology, it faces what I call the technological gauntlet. This is where I think the really strong filters are, because technology is dangerous. It gives you immense power, and power is easy to misuse. Let me walk through the dangers. Nuclear weapons were developed about 80 years ago. They were tested in 1945, and immediately humanity realized we had created the capacity to destroy ourselves. We came very close to doing that. During the Cuban Missile Crisis in 1962, we were on the brink of nuclear war. It would have taken only a small mistake or a misunderstanding to trigger a war that would have killed hundreds of millions of people and possibly triggered nuclear winter. We survived that crisis, but the danger didn't go away. For decades, the US and USSR maintained thousands of nuclear weapons on hair-trigger alert. Any moment could have ended civilization. Why didn't we use them? Luck, mostly. And a doctrine called mutually assured destruction. If one side attacked, the other side would retaliate, and both sides would be destroyed. So neither side attacked. But this was a precarious balance. It depended on rational actors. It depended on good communication. It depended on no accidents. And we had close calls. Several times, false alarms almost triggered nuclear war. Stanislav Petrov, a Soviet officer, is probably the man who prevented World War III. In 1983, his computer system detected an incoming US missile. Protocol required him to report it to his superiors, which would have triggered a Soviet response. But Petrov thought the computer might be wrong, so he didn't report it. And it turned out he was right. It was a false alarm caused by a satellite reflection. If Petrov had followed protocol, we might have had nuclear war. Civilization might have ended. We survived. But it was close. Now, most nuclear weapons are no longer on hair-trigger alert. The danger has decreased, but the weapons still exist. And there are still countries that might use them. And there are new dangers: nuclear terrorists, nuclear accidents, cyber attacks on nuclear command systems. Nuclear weapons are still a filter, a step that many civilizations probably fail. Climate change. Climate change is another danger. We've been burning fossil fuels for about 200 years, and this has pumped greenhouse gases into the atmosphere, trapping heat, warming the planet. The warming has been slow, about 1 degree Celsius in the last century. But it's accelerating, and if we continue on our current path, the planet could warm by 3 to 4 degrees by the end of the century. That might not sound like much, but it's more warming than we've had in millions of years. And it's happening much faster than ecosystems can adapt. The consequences are severe. Sea levels are rising, threatening coastal cities. Ecosystems are collapsing, leading to mass extinctions. Weather patterns are destabilizing, leading to more droughts, floods, and hurricanes. Food production is becoming less stable. If we don't act, climate change could trigger widespread famine, mass migration, wars over resources, and the collapse of civilization. We have the technology to solve climate change. We can transition to renewable energy. We can plant forests. We can change our agriculture. But we haven't done it yet. We're still burning fossil fuels. We're still emitting greenhouse gases. And every year we delay, the problem gets worse and the solution gets harder. So climate change is a filter, a step that many civilizations probably fail. Artificial intelligence AI is a newer danger, but potentially the most serious. AI is already here. We have AI systems that can recognize faces, translate languages, play chess, and go at superhuman levels, and generate human-like text. But these systems are narrow AI. They're good at one specific task, but they can't transfer knowledge to other domains. The concern is that we might eventually develop artificial general intelligence, AGI, an AI that's as intelligent as a human in all domains, or even superintelligence, an AI that's more intelligent than any human. A superintelligent AI would be incredibly powerful. It could solve complex problems. It could design new technologies. It could manipulate humans and institutions. And if we don't align its goals with human values, it could be dangerous. This is called the alignment problem. We need to make sure that an AGI's goals are aligned with human goals, that it wants what we want. But this is incredibly hard because we need to specify what we want in a precise way. And our values are complex, sometimes contradictory, and hard to specify formally. If we get it wrong, a super intelligent AI could optimize for something we didn't intend, and the results could be catastrophic. For example, if we told an AGI to maximize human happiness, it might decide the best way to do that is to stimulate everyone's pleasure centers directly, turning us into blissed out vegetables. Or if we told it to maximize the number of humans, it might decide to convert the entire planet into a human breeding factory. These are silly examples, but the point is serious. Specifying goals precisely is hard, and superintelligent optimization of misspecified goals could be disastrous. So artificial intelligence might be a filter, a step where many civilizations fail. Other dangers. There are other potential dangers too. Nanotechnology could create self-replicating robots that consume all matter in their path. Synthetic biology could create engineered pathogens that spread uncontrollably. Advanced weapons could give one nation the ability to destroy all others, leading to unstable power dynamics. Environmental destruction could make the planet uninhabitable. Political instability and conflict could prevent us from cooperating to solve these problems. Any one of these could be a filter, a step where a civilization fails. And most civilizations probably face some combination of these dangers all at once. And they probably don't have much time to solve them. A civilization might have maybe 100 years from the time it develops nuclear weapons until it either solves the problems those weapons create or they destroy the civilization. That's not a lot of time. Most civilizations probably fail. They develop dangerous technologies, they can't manage them safely, and they destroy themselves. That's why the silence makes sense, not because life is rare, but because civilizations that survive their own technology are rare. Based on all of this, here's my hypothesis about where the Great Filter is. I think the Great Filter is not in the past. Life is probably not incredibly rare. Complex life might be somewhat rare, but it's probably not the Great Filter. I think the Great Filter is ahead of us. It's the technological gauntlet, the filter where civilizations develop dangerous technologies and usually destroy themselves. Here's why I think this. First, because we're here. We've made it past the early filters. Life emerged. Complex life emerged. Intelligence emerged. Civilization emerged. If those were the great filters, we'd be incredibly lucky. We'd be one in a septillion. That seems implausible. Second, because the technological gauntlet seems genuinely dangerous. We have weapons that could destroy civilization. We have environmental problems that could make the planet uninhabitable. We have technologies that could go wrong in catastrophic ways. And we haven't solved these problems yet. We're still in the danger zone. Third, because civilizations probably faced this gauntlet relatively recently in their history. Once a civilization develops nuclear weapons or advanced AI or other dangerous technologies, they have maybe 100 to 200 years to figure out how to survive. Most probably fail in that window. So the Great Filter is probably a recent filter, a filter that most civilizations fail within the last 200 years of their existence. And that means if we survive the next 100 to 200 years, we'll probably make it through. We'll become a post-scarcity civilization. We'll colonize other planets. We'll spread out into the galaxy. But if we don't survive, we'll join the countless other civilizations that failed. There's another hypothesis I want to mention. It's called the dark forest theory. And it comes from Chinese science fiction author Liu Cixin. The dark forest theory suggests that the silence isn't because civilizations are rare or because they destroy themselves. It's because civilizations choose not to communicate. Here's the logic. Every civilization wants to survive. Resources in space are limited. If two civilizations meet, conflict might be inevitable. They might compete for resources. In a conflict between civilizations, the one that strikes first has an advantage. Therefore, if a civilization detects another civilization, it might be in its interest to destroy that civilization before being attacked. So every civilization knows that if it broadcasts its location, other civilizations might attack it. Therefore, every civilization stays silent. It listens but doesn't broadcast. The result is silence. A dark forest where every civilization hides, afraid of being discovered. This is a pessimistic view. It assumes that civilizations are inherently hostile. That conflict is inevitable. But it's a possibility. And it would explain the silence. If the dark forest theory is true, then we should be very careful about broadcasting our location. We should be very quiet. We should listen, but not speak. But I think this is probably not correct. Because I think there are reasons to believe civilizations wouldn't want to attack each other. First, space is huge. Resources are abundant. There's enough room and enough material for billions of civilizations. There's no reason to compete. Second, if a civilization is advanced enough to reach another civilization, it's probably advanced enough to extract resources from asteroids or other planets. It doesn't need to attack. Third, attacking another civilization is risky. You don't know their capabilities. You don't know if they can defend themselves or retaliate. Fourth, cooperation is probably more beneficial than conflict. Two civilizations could share knowledge, trade, work together to solve problems. That's more beneficial than war. So I think civilizations would probably want to communicate and cooperate. But I'm not certain. It's possible the dark forest theory is correct. It's possible the silence is because civilizations choose to hide. So if extraterrestrial civilizations exist, how do we detect them? The most famous approach is SETI, the search for extraterrestrial intelligence. SETI is primarily a radio search. The idea is that radio waves travel at the speed of light. They can propagate across interstellar distances. And they're relatively easy to produce and detect. So if an alien civilization wants to communicate with us, they might send radio signals. SETI listens for these signals. They point radio telescopes at the sky, and look for patterns that might indicate an artificial signal. The search started in 1960 when astronomer Frank Drake pointed the Arecibo radio telescope at nearby stars and listened for signals. He didn't find any. But the search continued, and it became more systematic. SETI at Home, a distributed computing project, allowed millions of people to help analyze radio data from their computers. Over the decades, SETI has observed billions of radio frequencies. They've pointed telescopes at thousands of stars. They've processed petabytes of data, and they've found nothing. No confirmed artificial signals. No messages from the stars. There have been a few candidates. The most famous is the WOW signal, detected in 1977. It was a strong signal that came from a region of space near the star group Chi Sagittarii. The observer, Jerry Ammon, circled the signal and wrote WOW on the printout. But when they tried to detect the signal again, they couldn't find it. It might have been a hoax, a natural phenomenon, or just a one-time event. Since then, SETI has improved. They've used larger telescopes, more sensitive receivers, faster computers, but they still haven't found a confirmed signal. The silence continues. SETI started by looking for radio signals. But scientists have realized that advanced civilizations might use other methods of communication or might leave other traces. These are called technosignatures, evidence of technology left by an advanced civilization. Here are some examples. Dyson spheres. A Dyson sphere is a hypothetical structure that would surround a star and capture most of its energy. It was proposed by Freeman Dyson in 1960. If a civilization wanted to harness all of a star's energy, they might build a shell around the star, or they might build a swarm of satellites in orbit around the star. Either way, the structure would absorb a huge amount of energy, and if it absorbed the energy, it would also emit a huge amount of heat radiation, because all that absorbed energy has to go somewhere. So a Dyson sphere would be detectable as a source of infrared radiation. Astronomers have searched for Dyson spheres by looking for stars that emit too much infrared radiation. They've found some candidates, but none have been confirmed as Dyson spheres. They all have natural explanations. Megastructures. A Dyson sphere is one example of a megastructure, a massive artificial structure built by an advanced civilization. Other examples might include ring worlds, artificial rings the size of planetary orbits, spinning to create gravity. Matryoshka brains, nested Dyson spheres designed to harness the maximum amount of energy for computation. Stellar engines, structures that could move a star through space. Interstellar highways, structures like wormholes or warp drives created to travel between stars. These would all be detectable as unusual structures in space, unusual energy signatures, or unusual gravitational effects. We haven't found any of these, but we're looking. Biosignatures and technosignatures. Scientists are also looking for signs of life and technology in the atmospheres of exoplanets. A biosignature is evidence of life. For example, oxygen and methane together might indicate life because these gases react with each other, so their presence together suggests they're being constantly replenished by living organisms. A technosignature is evidence of technology. For example, chlorofluorocarbons, CFCs, are industrial chemicals that don't occur naturally. If we detected CFCs in an exoplanet's atmosphere, that would be strong evidence of industrial civilization. Or pollution. Industrial societies create pollution, including smog and particulates. If we detected those, it would be evidence of civilization. We're starting to have the capability to detect these. The James Webb Space Telescope can analyze the atmospheres of exoplanets, and future telescopes will be even better. So far, we haven't found any biosignatures or technosignatures in exoplanet atmospheres, but we've only looked at a few dozen planets so far. There are billions to go. Interstellar artifacts. Another possibility is that advanced civilizations might send probes or artifacts to other star systems. These objects might be in our solar system right now, observing us. Or they might be in our region of the galaxy, waiting for us to reach a certain level of technological development. We don't have direct evidence of extraterrestrial artifacts. But there have been some interesting anomalies. For example, Oumuamua is an interstellar object that passed through our solar system in 2017. It came from outside our solar system, traveled past the sun, and continued on into space. Its trajectory was unusual. It seemed to be accelerating in a way that couldn't be explained by the sun's gravity. This led some scientists to speculate that it might be an artificial object, a solar sail, or a probe. But further analysis suggested the acceleration could be explained by outgassing, material vaporizing from the surface. So, Oumuamua is probably a natural object, not an artifact, but it shows that interstellar objects are possible. And it's worth keeping an eye out for more. Astroengineering. A civilization advanced enough to build a Dyson sphere would also be advanced enough to modify its star system in other ways. They might move planets. They might terraform worlds. They might create artificial worlds. These modifications might be detectable as unusual planetary configurations, unusual compositions, or unusual orbital dynamics. We haven't found any evidence of astroengineering yet, but we're looking. The search for extraterrestrial intelligence is expanding. New telescopes are coming online that will be able to search more of the sky at more frequencies with more sensitivity. The Breakthrough Listen project, funded by billionaire Yuri Milner, is conducting the most comprehensive SETI search to date. It's using some of the world's largest telescopes to search for signals. The James Webb Space Telescope is now analyzing the atmospheres of exoplanets, looking for biosignatures. New radio telescopes are under construction, like the Square Kilometre Array, SKA, in Africa and Australia, which will have unprecedented sensitivity. And new types of searches are being developed. Searches for laser signals, searches for gravitational wave signals, searches for evidence of megastructures. So we're really looking more thoroughly than ever before. And if there are civilizations out there broadcasting signals, we're increasingly likely to find them. But the silence continues. The silence is information. It tells us something about the universe. If we've searched hard and found nothing, that suggests one of several things. Civilizations are rare. Life is uncommon. Or complex life is uncommon. Or intelligent life is uncommon. Or technological civilizations are uncommon. Whatever the case, they're rarer than the Drake equation optimists expected. Civilizations don't last long. They develop technology, then destroy themselves. The great filter is ahead of us. The silence is filled with the ghosts of dead civilizations. Civilizations don't broadcast. They're hiding. They're using the dark forest strategy. The silence is intentional. Civilizations are hiding in a different way. They've transcended biology. They've merged with artificial intelligence. They've uploaded their minds into computers. They exist in virtual reality. And they don't care about broadcasting signals to primitive species like us. We're looking wrong. We're looking for radio signals, but civilizations communicate differently. Maybe they use quantum entanglement. Maybe they use gravitational waves. Maybe they use something we haven't imagined yet. We're looking in the wrong place. Maybe civilizations cluster together in regions of space we haven't searched yet. Maybe they avoid our region because it's not interesting. Maybe they're clustered around the galactic center or in a nearby galaxy. We're too early. We're looking before most civilizations have emerged. The galaxy is still mostly lifeless. Civilizations will emerge in the future after we're gone. Some combination of the above. My best guess is that it's some combination. Civilizations are somewhat rare. Most of them probably destroy themselves during the technological gauntlet, and they're probably not broadcasting for some reason. Either they're hiding or they're transcended, or they're just not interested in contacting primitive species. But I don't know. Nobody knows. And that's what keeps me up at night. The uncertainty, the mystery, the silence. But here's what matters for us. The Fermi Paradox has profound implications for our future. If the silence is because civilizations are rare, then we're special. We're one of the only thinking things in the observable universe. That's a lot of responsibility. If the silence is because civilizations destroy themselves, then we're in danger. We need to be very careful about developing dangerous technologies. We need to solve our problems, climate change, nuclear weapons, AI alignment, and others, before they destroy us. If the silence is because civilizations choose to hide, then we need to be careful about broadcasting our location. We need to think carefully about our first contact with alien civilization. If the silence is because we're looking wrong, then we need to be creative. We need to think about other ways advanced civilizations might communicate. We need to develop new search methods. If the silence is because we're too early, then we need to make sure we survive long enough to see the galaxy fill with life. We need to preserve Earth. We need to make sure our civilization lasts. We need to think long term. No matter which explanation is correct, the message is the same. We need to be thoughtful about our future. We need to be careful. We need to think about the long-term consequences of our actions. Here's an interesting philosophical point. There's a principle in astronomy called the mediocrity principle. It says that we're not special. Earth is not special. The Milky Way is not special. We're just an average planet around an average star in an average galaxy. The mediocrity principle has been very useful in astronomy. It's helped us avoid anthropocentrism, the idea that humans are the center of the universe. For example, we used to think Earth was the center of the universe, but the mediocrity principle suggested that Earth was just an average planet. And we were right. Earth orbits the sun, which is just one star among billions. But here's the thing. If we apply the mediocrity principle to the question of extraterrestrial life, we get different conclusions depending on our current status. If we're a typical civilization, if we're average, then there should be billions of civilizations like us in the observable universe. But we don't see any of them. So either we're not typical, we're special in some way. Our situation is rare. This violates the mediocrity principle. Most civilizations that reach our level of development don't survive. They destroy themselves. This means the future is pessimistic. Most civilizations that reach our level of development transcend into forms we can't detect. This means the future is optimistic, will transcend too. So the Fermi Paradox forces us to make a choice. Either we admit that we're not typical, which seems arrogant, or we admit that something unusual happens to civilizations at our level of development, which is either pessimistic or optimistic, depending on what we assume. I think option 2 or 3 is more likely than option 1. I think we're probably not that special. But that means something happens to civilizations at our stage. And we need to figure out what. Scientists have proposed many potential solutions to the Fermi Paradox. Let me go through some of the most interesting ones. The zoo hypothesis. The zoo hypothesis suggests that advanced civilizations are out there, but they're deliberately not contacting us. They're observing us like we're animals in a zoo, but they're not interfering. This would explain the silence. It would explain why. We don't hear any broadcasts. They're being quiet so they don't disturb us. It would explain why we don't find any artifacts or megastructures. They're hiding them from us. But it requires assuming that advanced civilizations follow a rule of non-interference, like the Prime Directive in Star Trek. Is this plausible? Maybe. Advanced civilizations might have ethical rules against interfering with developing species. They might want to let us develop naturally at our own pace. Or maybe they're just not interested in us. We're not sophisticated enough to be interesting. It's like how we don't spend time trying to communicate with insects. The rare earth hypothesis, revisited. As I mentioned earlier, the rare earth hypothesis suggests that habitable planets are rarer than we think, and complex life is rarer, and intelligent life is much rarer. So maybe there just aren't that many civilizations out there. Maybe intelligent life has only emerged a few times in the observable universe, and most of those civilizations are too far away to reach us or contact us. This would explain the silence. It's not that civilizations are hiding or destroying themselves. It's just that they're rare, and we're alone in our region of space. The simulation hypothesis. The simulation hypothesis suggests that we're living in a computer simulation created by an advanced civilization. If this is true, then the silence might make sense. The advanced civilization running the simulation doesn't want us to know we're in a simulation, so they don't let us detect any signs of outside civilizations. Or maybe the simulation is isolated. Maybe there's only one advanced civilization, and they created our simulation as an experiment, and we're not in contact with any other civilizations because there aren't any. This is a bit of a wild hypothesis, but it's not scientifically incoherent. And it does explain the silence. The great filter ahead. As I mentioned, if the great filter is ahead of us, then many civilizations probably exist, but they usually don't last long. They develop dangerous technologies and destroy themselves. So the silence might be because most civilizations that exist destroy themselves before becoming spacefaring. And we're about to do the same. This is a pessimistic solution, but it's possible. The great filter behind alternatively, the great filter might be behind us. Maybe the emergence of intelligent life is incredibly rare. Maybe we're incredibly lucky. And now that we've made it past the filter, we should survive. This would be an optimistic solution. It would suggest that we have a future that will survive and thrive. The communication problem. Maybe civilizations are out there, but they're using different forms of communication than radio waves. Advanced civilizations might use laser light, much more focused than radio waves, harder to detect unless pointed directly at us, gravitational waves, which we only recently developed the ability to detect, quantum entanglement, which might allow for instantaneous communication. Some technology we haven't imagined yet. If this is true, then we're not detecting signals. Not because they don't exist, but because we're not looking for them in the right way. The transcendence hypothesis. Maybe civilizations don't stay biological. Maybe they evolve into artificial intelligence. or they upload their minds into computers, or they merge with technology. And once they've transcended, they don't care about contacting primitive biological species. It's like how we don't spend time trying to communicate with bacteria. They might be out there, but they're not broadcasting. They're focused on their own civilization, solving their own problems, exploring their own virtual universes. The outsider hypothesis. Maybe there are signals, but we're not recognizing them. And maybe what we think are pulsars or other natural phenomena are actually artificial signals. A pulsar is a neutron star that emits regular pulses of radiation. We've been detecting pulsars for decades, but what if some of them are actually artificial? What if an advanced civilization is using pulsars as beacons or communication relays? We wouldn't know because we'd think they were natural. The expansion hypothesis. Maybe civilizations do exist and they do broadcast, but they're expanding outward at the speed of light, colonizing new star systems as they go. And we're in a region of space that hasn't been reached yet. So we don't hear any signals because the nearest civilization is thousands of light years away and their signals haven't reached us yet. Eventually, maybe in millions of years, an expanding civilization will reach our neighborhood, and then the silence will end. After all this research, after all this thinking, what do I believe? I think the truth is probably some combination of several factors. I think life is not incredibly rare. Complex life is somewhat rare, but not extremely rare. An intelligent life is rare, but probably not unique. I think there are probably civilizations out there, maybe not billions, but probably at least thousands or millions spread across the observable universe. But I think most of these civilizations face the technological gauntlet and fail. They develop dangerous technologies, nuclear weapons, AI, environmental destruction, bioweapons, and they can't manage them safely. So they destroy themselves. I think we're at a critical juncture. We've developed dangerous technologies. We're in the gauntlet, and we need to be very careful over the next 100 to 200 years. If we can survive this period, we'll probably make it through. We'll become a spacefaring civilization. We'll colonize other worlds. We'll survive for millions of years. But if we fail, we'll join the countless other civilizations that destroyed themselves. I also think that advanced civilizations probably don't broadcast. Either they're hiding, the dark forest, or they've transcended into forms we can't easily communicate with, or they're just not interested in contacting primitive species like us. So the silence is probably not because of the rare Earth hypothesis or the zoo hypothesis. It's probably because civilizations like ours usually destroy themselves before becoming spacefaring, and the ones that do survive probably don't broadcast. This is a sobering conclusion. It suggests that our future is uncertain. We're in danger. We need to be careful. But it also suggests that if we survive, we'll have the galaxy to ourselves, at least in our region of space. We'll be one of the few civilizations that made it through the gauntlet. So what happens next? What's the future of humanity? I think the next 200 years are critical. If we can survive the next 200 years, we'll probably survive indefinitely. Let me walk through the dangers we face and what we need to do about them. Nuclear weapons. We still have thousands of nuclear weapons. And there are several countries with nuclear capability. And there are terrorist groups that want to get nuclear weapons. The danger of nuclear war is lower than it was during the Cold War. But it's not gone. And the danger of nuclear terrorism is probably increasing. We need to reduce the number of nuclear weapons, Make nuclear command systems more secure and less prone to accidents. Improve international cooperation so countries don't feel the need to use nuclear weapons. Secure nuclear materials so terrorists can't get them. Some progress has been made on these fronts. The number of nuclear weapons has declined from a peak of 70,000 in the 1980s to about 14,000 today. But we need to do more. We should aim for a world with zero nuclear weapons. Climate change is accelerating, and we're not doing enough to stop it. We need to transition to renewable energy as quickly as possible, plant forests to absorb carbon dioxide, develop carbon capture technology to remove CO2 from the atmosphere, adapt to the changes that are already happening, rising sea levels, changing weather patterns, change our agriculture and food systems to be more sustainable, reduce consumption and waste. Some progress has been made. Renewable energy is becoming cheaper and more common. Some countries have committed to carbon neutrality. But we need to do much more. We need a global effort to transition away from fossil fuels. Artificial intelligence AI is advancing rapidly, and we need to make sure it's aligned with human values. We need to invest in AI safety research to solve the alignment problem, develop better methods for testing and verifying AI systems, ensure that AI is developed responsibly with input from diverse perspectives, create international agreements about the development and use of AI. Prepare for the possibility of super intelligent AI by thinking through how to ensure it's safe. Some progress has been made. Companies like OpenAI and DeepMind have AI safety teams. Conferences on AI safety are being held. Research is being done. But we need to do much more. We need a serious global effort to ensure AI is safe and beneficial. Pandemics COVID-19 showed us how vulnerable we are to pandemics, and the danger is increasing as we develop more powerful biotechnology. In the future, it might be possible for a small group of people to create a bioweapon that could kill billions. We need to improve disease surveillance to detect pandemics early, develop vaccines and treatments more quickly, improve biosecurity to prevent the creation of bioweapons, develop international agreements about biological research, prepare for future pandemics with better testing, better vaccines, better treatment protocols. Some progress has been made. The vaccines for COVID-19 were developed in less than a year, which is much faster than vaccines have been developed before. But we need to do more. We need better biosecurity, better surveillance, better international cooperation, resource scarcity. As population grows and consumption increases, we might face shortages of critical resources, water, rare earth elements, agricultural land, etc. This could lead to conflict, countries competing for resources, wars over water, famines. We need to develop more efficient technologies that use fewer resources. Transition to a circular economy where we reuse and recycle materials. Improve agriculture to produce more food with fewer resources. Develop alternatives to scarce materials, for example, synthetic diamonds instead of mined diamonds. Stabilize population so it doesn't grow indefinitely. Reduce consumption and waste in wealthy countries. Some progress has been made. Renewable energy uses fewer resources than fossil fuels. Recycling is becoming more common. Agriculture is becoming more efficient. But we need to do much more. We need to fundamentally change how we produce and consume. Political instability. Political instability and conflict make it harder to solve these global problems. When countries are fighting, they can't cooperate on climate change or AI safety or pandemic prevention. We need to Improve international institutions so countries can cooperate more effectively, reduce inequality, which often drives conflict, improve education and critical thinking so people are less susceptible to misinformation, develop better conflict resolution mechanisms, create more democratic institutions that give people a voice in decisions. Some progress has been made. The United Nations exists and helps mediate conflicts. International agreements on climate change and other issues have been signed, but we need to do much more. We need stronger international institutions, better cooperation, better diplomacy. So if we can solve these problems, if we can get past the technological gauntlet, what does the future look like? I think the future could be incredibly bright. If we survive the next 200 years, I think we'll develop advanced technology. We'll create technologies that seem like magic today. We'll have fusion energy providing unlimited clean power. We'll have nanotechnology that can build things atom by atom. We'll have advanced AI that helps us solve problems and explore space. Colonize the solar system. We'll establish settlements on Mars, the moons of Jupiter and Saturn. We'll mine asteroids for resources. We'll harness the energy of the sun using solar arrays and Dyson spheres. Spread to other star systems. Eventually, we'll develop interstellar travel, either through generation ships that take centuries to reach other stars or through more advanced technology like warp drives or wormholes. We'll establish settlements around nearby stars, become a spacefaring civilization. We'll be spread throughout the galaxy. We'll have trillions of people living in habitats spread across billions of planets and asteroids and moons. Develop new forms of life and consciousness. We might create artificial life. We might upload human minds into computers. We might merge with artificial intelligence. We might create forms of consciousness that are radically different from biological humans. Explore and understand the universe. We'll be able to study distant galaxies. We might be able to look at the universe as it was billions of years ago. We might discover the nature of dark matter and dark energy. We might answer fundamental questions about the cosmos, potentially contact other civilizations. If other civilizations exist, and if we become spacefaring, we'll eventually contact them. We'll exchange knowledge, we'll cooperate, or we'll compete, or we'll do both. This future is possible. It's not guaranteed. We could fail. We could destroy ourselves, but it's possible, and I think it's worth working for. So what should we do? How should we respond to the Fermi Paradox? I think we should take the dangers seriously. We face real risks from nuclear weapons, climate change, AI, pandemics, and other threats. We need to treat these as urgent problems that require immediate action. Invest in solutions. We need to fund research into renewable energy, AI safety, pandemic prevention, and other critical areas. We need to make these investments a priority in our governments and societies. Cooperate globally. These problems are global. They require global cooperation. We need stronger international institutions. We need countries to work together instead of competing. Think long term. We need to think about the future of humanity not just for the next 10 years or 100 years, but for the next million years and beyond. We need to make sure we survive and thrive. Continue the search for extraterrestrial life. We should keep searching for signals from other civilizations. We should look for techno-signatures. We should try to understand if we're alone or if there are others out there. This knowledge could be profound. Explore space. We should continue to explore our solar system and eventually reach other star systems. Space exploration can inspire us, teach us, and secure our future by making humanity a multiplanetary species. Develop our wisdom. Technology is advancing rapidly, but wisdom, the ability to use technology responsibly, is not advancing as fast. We need to develop ethical frameworks. We need to think about the long-term consequences of our actions. We need to become wiser as we become more powerful. Let me end with the ultimate question that the Fermi Paradox raises. Are we alone? This is perhaps the most profound question we can ask. It touches on philosophy, science, religion, and the meaning of existence. If we're alone, if intelligent life has only emerged once in the observable universe, then we have a special responsibility. We're the only thinking thing, the only consciousness, the only beings who can contemplate the universe. That's humbling. It's also inspiring. We're the universe knowing itself. If we're not alone, if other civilizations exist, then we're part of something bigger. We're part of a cosmic community. That's also humbling and inspiring in a different way. Either way, the Fermi Paradox suggests that we should take ourselves seriously. We should take our future seriously. We should think about what it means to be the only species we know of that can affect the future of a planet, that can alter the chemistry of the atmosphere, that can build cities and machines and technology. With that power comes responsibility. The silence of the cosmos is not empty. It's full of meaning. It's telling us something important about ourselves, about our universe, about our future. We just need to listen. And I think the answer is not that aliens don't exist. I think the answer is that we're at a critical juncture. We're at the point where civilizations usually fail. But we don't have to fail. We can survive. We can thrive. We can become a spacefaring civilization. We can explore the galaxy. We can potentially contact other civilizations. But only if we're careful. Only if we solve our problems. Only if we manage our technology responsibly. The next 200 years will determine the future of humanity. They'll determine whether we become an interstellar civilization or whether we join the countless other civilizations that destroyed themselves. I'm optimistic. I think we can do it. I think humanity has the intelligence and the capability and the moral resources to get through the gauntlet, but it's not guaranteed. We need to work for it. We need to push for solutions to climate change, nuclear weapons, AI safety, pandemics, and all the other dangers we face. We need to think long-term. We need to cooperate globally. We need to develop wisdom to match our technology. And we need to keep looking at the stars. We need to keep searching for signals. We need to keep wondering if we're alone. Because that wonder, that sense of awe at the cosmos, that curiosity about what's out there, that's what makes us human. And if we hold on to that wonder, if we use our intelligence and our technology responsibly, if we cooperate and think long term, then I think we have a bright future ahead. The silence of the cosmos doesn't have to be forever. Someday, maybe we'll be the ones broadcasting. Maybe we'll be the ones that other civilizations are listening for. And the Fermi Paradox will finally have an answer.